when you talk about the multi-dimensional index, I'm not going to spend a long time. Just give you an idea, then that's going to depend on you, okay? Usually, I don't cover this one in more details, but I will give you an idea about the multi-dimensional index, or multi-dimensional, how it works. Then you give you some examples, give you some links, and it depends on you. It depends whatever database management system you prefer to use. You need to take a look to database management system that you use in order to see how can you utilize them. This is your chance in order to see different indexing techniques. It might be that might be some of them you are not aware of them, so it's gonna help you at least maybe when you build an index based on the data that you have. So maybe you know exactly what kind of index you need to build in order to catch or maybe in order to perform the overall performance. So I will go over several, as I mentioned, some additional additional index use. Okay. Then after that, we're gonna talk about different types of index, tries or radix. Inverted index, I will cover this one more details a little bit. Then after that, show you the different ways to remember. We have multi-level index is not working, single dimensional index is not a good idea. So how can use different techniques in order to allow me in order to use or index the data that contains 2 or 3 dimensions. For example, let's see. Assume that we have a map, and map that have like point of interest. Okay, hotel, restaurant, etc. Then you need to perform this kind of query. For example, I'm looking for the nearest, so let's say, restaurant to my location. So what kind of index you need to build in order to help you in order to access, expedite, or retrieve the information that you're looking for in a faster way? Okay, so all the information can be in the X and Y axis. So we're going to show you a different way in order to store the information in the way that the information that close to each other can be represented or stored in the same block or the nearest block to each other. Because if you store the information in 2 different index based on X and Y, you cannot guarantee that the information or the locations or the point of interest that locate each other or close to each other is going to be stored in the same block or in the, let's say, nearest block. Okay? Anyway, we're going to show you different algorithms or technique or index. Then after that, we're going to take a look at the bitmap index. Which one interesting right here. We're going to see how can we use this one. Okay? So the simple thing here, I'm going to show you what do you mean by the endless index. Let me ask you a question. Without looking here, if you create this, you create a table, and the name of the table is full, for example, and you have the ID serial, whatever you define, for example, a set of attributes like a primary key and unique. Do you need, without reading this slide, just I want to see whether we are on the same page or not. Do you need to create index based on the ID and the val true or not? For example, we wish to have an index. So what I have to do here? Do you have to create, for example, unique index blah 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 and unique index blah 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 based on the public key and based on the val true or not? I mean manually. You have to type this one manually. No. Why? I want to have index based on the primary ID and val true. So if I don't create them, so who's going to create them? Exactly. So the most of the system, okay, automatically when you define, let's say, ID as a primary key or any attribute as a primary key or as unique, the system automatically going to generate what? It's going to generate like index for this one. So it looks like in this case, the system going to automatically say, okay, create unique index, and it's going to choose the name. It's going to be mixed between the relation name and the data types of the attribute. Okay, and sometimes it's going to have, for example, if unique, it's going to say what? It's going to be the relation name and the attribute name and the data type of the attribute. Okay, whether it's going to be key or not. Okay, on and the name, the relation name, and the ID. This is the system going to be automatically generate this one to us. Okay, I will give you an example here after we finish this different type of additional index usage. I'm going to try to test this one with the Postgres. I'm going to show you when you create this one, check the index, and you're going to see the index out there. because I know that I'm not you. There's few students. What they're doing here, when you or the few users, when they're doing create this, they're gonna create another index and use different names of the index. So you have more than 2 index. For example, for every primary key, we do have one extra index that's gonna be just generated, just created, which we are not gonna use. Okay. So again, keep in your mind for the primary key unique constraints. The database management system is gonna create an index automatically. So if you have example here, how about, let's say, the foreign key constraint, because it's kind of constraint, a short constraint. Can you do this one? No, the system is not going to do this one, okay? So what we're going to do in this case? So it's not going to create this one automatically. So assume that we have this relation, okay, or this table, the same one, okay, and they do have another table, okay, this bar. And here they said the ID here is going to reference what? The ID of the other relation, reference to. Okay, the val1. The val1 is not created as what? Let's say it's not a primary key, it's not unique. Let me go back to the previous slide, then I will get back here. Why we need to create an index for the primary key and the unique? For the reason behind this one, the database management system needs to find a way in order to enforce the integrity constraint. So in this case, every time if you try, for example, insert a new data, says ID equal 1, okay, and the rest I don't care, okay. Then after that you said ID, you insert ID again 1. How the system can tell whether the IDs exist or not? So it must have an index. Based on the index, it's gonna be enforced. It's easy to check the index to find the ID values already exist. Then you're gonna produce like an error message, for example, violation, let's say the integrity constraint, and give you some error message. So that's how they enforce. What's called the integrity constraint. If there's not, we don't have index. That's the only solution here to scan or perform sequential scan to entire data, trouble blocks or the contains information. Then it's gonna cost time, spend long time in order to just to tell whether it's allow me to perform this operation or not. The same thing in the referential integrity. When you try to enforce this one, I'm gonna talk about the foreign key integrity here. This means it's gonna be point to the unique value or the primary key in general. So when you try to perform this one, I don't have a tool. In order to perform this operation, you have an error here, okay? Because in order to have reference one ID or we'll say attribute, reference to another attribute to other relation, that relation must have an index in order to enforce the integrity constraint at that on this attribute in this relation. So if you try to perform this operation, it's not working. We can work and do what? Unless you create an index based on the val1 here. If you create an index based on the attribute that you use as a reference attribute, then in this case, the system, yes, this one is going to be perfect. There's no problem. There's no error message. Okay? So that's a simple thing you can do here. Or someone has said, okay, I'm going to define anything, an attribute used as, let's say, foreign key constraint, because I don't want to keep tracking every single foreign key, let's say, attribute used as a foreign key in order to what? Reference as a, to, let's say, reference to as a foreign key in order to generate index by myself. Let the system do this one automatically. So I'm going to assign out data type to all the attributes used as a foreign key as, let's say, unique. Okay? Which make our life easier here. Okay? So in this case, there's no need to do index, because when you create a table, the index or the system automatically is going to create index associated with every single attribute defined as, let's say, unique or defined as primary key. Why? In order to enforce the integrity constraint associated with this one. Okay? Another thing we call the partial key here. So what does that mean? So in many situations here, as a user, maybe you want or you don't need to have an index for every single tuple in the relation. So assume that we have this data, okay? And I have, for example, names. Or let's say department. This better department. Okay? And computer science, math, blah, blah, blah. A lot. I don't want to build index based on all the department. I'm just interested to build index based on the computer science department. So it can come up with what is called the partial index. So in this case, it looks like you build index based on this attribute. Okay? So it looks like only subset of the data, not the entire data. So how can you perform that? You can do the same thing. You can do what? Create index, name of the index, on specify what relation and the set of attributes you're gonna build the index, and you're gonna add the where clause. By adding where clause, this means the system gonna say, you're gonna build what? You're gonna build, say, a partial index, not the entire index. Okay? And I give you here, I'm adding this link below each slide in order to give you more details. If you want to learn about the partial index, for example, as example, I've used only Postgres. I cannot go over every possible database management system. So it depends on you. Whatever database management system you're interested to work with, or the one that you usually work with, go there and check whether they have partial index or not. Sometimes maybe have a different names, but most of them they're going to use the partial index as a name in order to identify this kind of operation or this kind of index. So anyway, so by adding where clause, this means in this case I'm filtering every single possible tuple. I filter out only the tuple that have computer size. I use this one. I build the index in the base on the top here. The size of the index is might be much less, smaller, and it came in the handy later. For example, if you work, let's say, in the big organizations, and generally speaking, you extract the data based on the bare month or based particular say year, etc. So it's easy to what? It's better to organize or build index based on the monthly base. For example, May or June or July or December, because December we need to collect all the information that, or you say financial data that belongs to a specific month in order to expedite the access to the data. And this is only the portion of the data that I'm interested on. So you can build the same month from January to December. So I have 12 index, and each index you can, based on the data that you're looking for, the system can know, for example, which index you're going to use in order to expedite access to the data. And this is great because the size is going to be much less. Okay, good. So now we have a query like this: select B from the relation where A equal whatever the value, and the C is equal Alice. Sorry. I teach in the morning CS525, and we use alias as a name in order to identify or rename the name of the relation and attribute. So pardon me. Okay, so here we created based on the Alice, let's say based on the department, for example, computer science, to have the same one. So here in the system, or the database management system, we're going to say, okay, it looks like this one, you want A and B. I do have an index that contains the value of A and B. You want a B, and you give me the value of A, so I can use this one in order to access the data. And the nice thing here, you give me the C equal computer science. So I know that they build index based on specific value, what's called a computer science, so I can use this index. So if you use this one different value, for example, C equal math, the system is not going to be able to use the index because it doesn't match. This one must be computer science or must be else in order to use the exact index. This is what we call the partial index. Okay? The other type of index, or other implementation database can do in order to speed up the access to the data is called covering index. Okay? So what does that mean here? Sometimes, as actually this situation here, let me go back. All the attributes that you need is available in the index. So do you need to go back to the disk in order to extract the data? No. There is no need in order to perform this operation. Right? Because, I mean, why you need to access the data? Okay? Why you need to go access, for example, let's say to the actual data while I'm still being able to answer the query based on the index? Okay? That's what we call, covering indexing. So in this case, I can build my index, whatever the value, A and B or whatever. Then the system will check if all the information that you need can be retrieved from the index. This is what we call, covering index. In the Postgres, they use this one different name. They call this one index only scan. Actually, you can, on the covering index, they have the same name. Yeah, so they call index only scans. One thing I need to add here for the Postgres, some database management systems do something weird. It's not weird, but the way that organize the data. So here, it's gonna build the index, okay? And at the lower level, they store what? The data is gonna be stored in the heap, okay, or the table heap. So the information, that means what? When you access and index, okay, or perform index scan. When you say index scan, you're gonna check this one or talk about this one later when you talk about or cover the query optimization or processing. You see that, for example, how can we access the data? We have a different way, sequential scan, or one way is gonna use what we call index scan. I'm gonna use index in order to tell me or access the data, tell me where or how can you fetch the tuple from the data, from the relation. Okay, so anyway, when you perform this, what you call index scan, okay, each tuple is going to require what? If you find, for example, whatever index that I have, okay, assume I have, let's say, tuple here, and this is the data that you want to access. This is not eyes, okay? So in this case, when you try to perform or fetch the data, this requires from you to what? You are going to fetch the data from what? From two things, from the index and the heap. How? I need to look up the index first to identify, tell me where where I can find my data that I'm looking for. Then after that, you have to follow this pointer to the heap file, or the way that, or heap table, with the way it's going to be organized randomly. So we cannot guarantee the order here. We don't have like order preserver. For the Postgres, all the data can be stored at the lower level as a heap table. And the top is going to be indexed, but we cannot guarantee the order is going to be the same. So they have different techniques in order to perform that. For example, I can monitor, for example, say, since you are going to access multiple data, for example, you need, for example, block 1, then after that, block 5, then you need to access block 1, then a block 6, then a block 1. So what I'm going to do, I'm going to organize the data, order them, and say, now I will access block 1. I will give you all the blocks, or the tuple that you want from block 1. Then after that, I'm going to access block 5 and give you all the tuple that you want in order to organize the data. Okay? Anyway, so that's what you call a covariant index, or let's say you can index only scan. The other type of index we can use here is called like index, what's called index include columns. So in this one, I can add include here. So what does that mean here? We can modify our index, okay? Since the higher level, let's say the inner loop, nodes, it's gonna contain a part of the key, or the search key, or you see the keys that you use in order to what? Traverse or navigate my way from the top until I reach the leave node. So what I'm going to do at the leave node, I'm going to add extra attributes. This attribute is not going to, or set of attributes. There are, or if one or more, let's assume for simplicity, I'm going to add extra attributes, okay? Assume that you build index base A and B, okay, from the high level up to the low level. In the leave node, I'm going to include C. The value of C. The value of C is going to be what? Only it's going to be in the leave node. But we are not going to use this one in the where clause. In order to determine, for example, let's say where clause, when a where clause, I'm not going to use this one in order to navigate my way from or use it in the search to find where I'm going to left or the right until reach the leave node. Okay? So it's not going to be part of the search key that I'm going to store in the inner loop. That's what you call, column. You can do this one using the the Postgres. If you take a look at the one option here, allow you to have include. So you can include or add one set of attributes, one or more attributes, and going to be part of the leave node, but then it's not going to be part of what is called the search key. You remember the search key that you use the components that are stored in the index entry? We do have a search key, then you have a pointer. And the search key is going to be A and B, and C is not available, it's not part, but only it's going to be in the lower level. Okay, so we can create index normal way on attribute A and B. I'm going to include C. So C is again, this is only going to be stored in the leave node, but is not going to be part of the search key. Okay. Based on the description of Postgres, I like this one. They said the optional include clause specifies a list of columns which will be included in the index as non-key columns. So use this one and it's not going to be non-key. So in this case, the system, if you have like select whatever from A equal blah 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 and C equal else, you build the index space. You include C as a leave node, extra piece of information. So the system, when you start looking at the tree, so here in the high level until leave node, I'm going to use based the value A and B here. So here I give you value of A. So looking for A equal 1, 2, 3. Go left, right, left, right, left, right. Now in the leave node. In the leave node, when you fetch this one, now you're going to find a value of A 1, 2, 3, different value of B. Then we have value of C equal Alice, or different value of C here. So you can check the value of C to see whether the value of C equal Alice or not. If Alice, then you're going to project B. So it's going to help us, which is interesting. It's going to be, because I can add any columns. I don't need to use them in the search key, but it's going to help me. And in this case, I don't need to fetch the data from where. I'm still doing what you call index-only search, yeah, or scan, because I'm not going to fetch information from the desk, or let's say from the heap file or the table. I'm just get all the information that I'm looking for. It's going to be available from the index that we have. You see that we have a different way to optimize command in order to fast access to the data or speed up the access to the data. Okay? The other type of, you say, optimization can database management system do based on the index, or alternative another index. I can build the index based on what? Based on functional or based on the expression. Yeah, you have a different way. So instead of doing like lookup on the exact value of the search key, whether A equals something, or looking for example, I'm building my index based on the A. So here I'm going to say where A is equal whatever, exact value. Oh, I'm looking for the entire value of A. Okay? Of course, you can use like and such, it depends. But right now, I'm not the actual value of A. So how about, I'm not looking at, when you say the actual value, that means the value or attribute A is the exact, going to be stored in the disk, on the table, on the file. Okay? I'm not interested in the A. Maybe I'm interested, for example, at the average, or say A, better build our index based on the salary. Salary equal greater than whatever, okay? So that means we do have like a salary column that's stored in this relation. I'm not interested to search based on the actual data, how it's stored in the disk, or stored in the disk, on the table. I'm interested to perform like an operation, to say function, average, for example. I need to search, for example, where the average of the salary. So if you take a look at the database, the actual data, you are not going to find the column, you are not going to find this piece of information. So you have to compute it. Okay? So in this case, we can use index, which can be created based on the function. Okay? So when you build index based on the function, that means here, we are going to perform the lookup based on what? Based on the some value that we can derive from whatever the key or an attribute stored in the relation. Okay? So take a look here. When it says select to start from the users, for example, you will extract the day of a week from, let's say, login equal to. And you know, the day extracted like the function that allow you what? Retrieves, for example, an attribute, and you can specify what kind of attribute you can retrieve from the field. You can retrieve, for example, a year, month, a day, a time, etc. You know that. So generally speaking, we can use this one like extract, and you can specify an attribute, then specify from, and you can, let's say a function or say a field from an attribute. This is the way that we use this one. So you can extract, and you have like a field from, this is an attribute that you want. And here you have many values, okay? You can have, say, many of them, okay? Day of the week, day of the year, a month, century, etc. Year, etc. Extract from, let's say, timestamp information, if you wanted to do this one. So the day of the week is like, if you remember this one, it's going to be Sunday, it's going to be 0, and Saturday, it's going to be 6. Yeah, from 0 to 6, starting from Sunday. So, for example, 2, that means 0, 1, 2, 3, Sunday, Monday, Tuesday, Wednesday, Tuesday, yeah. So that means I'm looking for what? I'm extract all the people or the users that access or log in on Tuesday. That's the meaning here, okay? So how can you perform this one? So login, of course, is going to be contains information about the timestamp in general. So you can extract the information. So assume that in this case, this is my query, and assume that I'm building, or we do have index like this. I'm building, maybe I already have index based on the login information. So the database management system is going to check or take a look at the query. Okay, you said where extract day of the week from blah blah login. I know you do have index based on login, but this is not good because it's not going to help me. I don't need to access the login Excel. I need to access and perform some operation, some expression. So the database management is not going to use this index in order to perform the query. So in order to make sure the database is going to work with this one, so what I'm going to do here, I'm building my index based on, let's say, a function or the expression. So here, create index, whatever the name, on the name of the relation, And here specify and what? The attribute is going to be extract day of the week from the login. So here it's going to be 2, 3, 0 up to 6. This is the unique value, and then we're going to have the pointers, whatever, on top of that, associated with this value. Then now when you write your index or execute this, the query here, the system is going to say, of course, as I mentioned, we cannot guarantee 100% because it depends on the data. Maybe the indexer say, or the database management system decide, as we're going to see later, okay, you are going to only access only 2 blocks, or the first block or the second blocks. Why am I wasting my time? Well, I'm going to perform fetch index, and after that, and end up to access one discount out operation. Or all your data stored in 1 block, so I'm going to perform sequential scan, because regardless whatever data that you need to retrieve, you're going to access only 1 block. Okay? Anyway, so assume the data are going to say, okay, we decide to use index. This is the index that's going to be used. Okay? We can achieve this goal the same using the partial index. Yeah. This is one other way. Create index from the full way, and going to build the index base that extract this information. The day of the week from this one. Okay? So it works in this case. Good. Any questions? As you mentioned, I know, I'm sure that you're aware of all these, let's say, optimization that database management systems can use regardless of the index, different way to build the index in order to speed up the access to the data. Okay? So far so good, guys. So take a look, you have one observation here. We're generally speaking here, we look at the P+3 in general, okay? And based on the index, the structure that we have here, can you tell, based on the inner loop, whether the keys exist or not, by looking only to the inner loop, any nodes? I don't know why the inner loop, because I was talking about the sub-queries today. Anyway, by looking to the inner nodes that we have in the P+3, can you tell, can you decide whether the key exists or not in the index? We can't, yeah? Because we cannot guarantee. You see, sometimes you're going to see the inner node is going to contain what? Some maybe values for the search key that we deleted, but since it depends based on the way that you perform redistribution and merging, etc., maybe we don't need to propagate the change to the higher level, because maybe we delete one entry from the lower level, from the leave node, and the search key here from the leave node does not exist anymore. But when you delete this one, doesn't cause, the node is going to be turned to be like underflow, which require for me to handle that. No. So you see that even in the quiz, if you look at this one, you see that some search key, when you delete it, or some search key exists in the higher level, but does not exist in the lower level leave node because of this. So anyway, by looking to the inner nodes, I cannot tell whether the keys exist or not, unless I reach to the leave node. Now we're going to perform. I can't tell you whether the keys exist or not. So what I'm planning to do here? Oh, before doing this one. So sometimes you can have what you call one, let's say, mess in the buffer pool. For example, because you need to fetch the data, it depends on the buffer pool that we have here. So the buffer pool allow me only 3 blocks. Maybe the buffer pool is like 4. Okay, so you try to 4. So you need to fetch, let's say, the leave node here. So one mess here. Then after that, you need to fetch this either left or the right. It depends on the search key that we have. So there's a chance, or might be the chance, you have at least one mess per block or per level when you try to access to the, or find out or traverse your tree from the higher level to the lower level. So what we're looking for? If we have to find a way that just by looking to the tree or the inner node, the nodes, I'm not going to need to go to the lower level or the leave node. If we can see or tell whether the keys exist or not, it's going to be great. Yeah, it's going to save us time, because remember, the information is just looking by the, let's say, the inner nodes, and you can decide whether the keys exist or not. That's going to be great. Or at the beginning of the tree, in the root, or maybe to the first 2 levels. If we can tell whether keys not exist or not exist, that's going to be great. So that means I don't need to waste my time to go or fetch too many or balloon the buffer pool and end up at the end to the leave node and say, oh, the keys not exist. Okay? So we're going to talk about what is called the try index. I think you study this one in the data structure. You call this one the prefix tree, if you remember that, this one part. So the try index is what? It's like one index of data structure which allow us to know that to perform what? in order to tell by just looking at the top of the tree whether the keys exist or not. It's going to be great. Okay? So generally speaking here, when you work with it, I mean, the trie starts at the top. And the way that it's going to be built is a data structure, a tree data structure. So the structure somehow is going to be a tree, but it's not like the tree that we know here. So it's going to have what? It's going to be branching at any level, okay, from the top and the low, okay, it's going to be determined by what is called one digit or only one digit of the key at the time in each level. So what do you mean one digit? Digits, when you could, that means subset of the key. Maybe it's going to be bits, maybe single bit or number of bits, maybe bytes, or maybe character for simplicity if you try to say. So we start at the top in the level, okay? We're starting to store them for, I mean, I'm not going to store, the entire level from any leave node, non-leave node, okay? So we're starting from the top. I'm going to take whatever the key or the search key that you wanted to store. I'm going to decompose this one into what? Into based on, to say number of digits or the set of characters, and I'm going to store in each level one character. Okay? So we're going to store this one, we're going to them down until each, the leave node. So if you have a multiple or duplicate digits that belong to different search key, I'm going to store only one of them. So we start, for example, if you have hello, hat, and have, so I'm going to decompose each of them. The first letter H, so we start H. Then the second level or the second digit is going to be E, and we have A. So we can here distinguish this one between two things. It's going to be branching to the lower level. So I'm going to start A and E. Okay, since we have two A's, duplicate, I'm going to store only one of them. Then, now we'll focus on this one, because now we're branching to the left. We do have LL, okay? So this one, L, L, O. We don't have any options here. For the hat or have, we do have T and V. So it's going to be further divided or branching to two parts, T and V, and etc., okay? And at the end, we have a pointer to whatever the data that we're looking for, the actual data. This is how to build the prefix tree. So again, decompose all the keys and store them down the digits, okay? Different level one by one. If you have a duplicate value, then you store only once of them. Okay? So how can you search looking for data? So for example, you're looking for cat. You start at the top. C is not exist. Cat is not exist. There is no need to fetch the whole thing. You can tell from the top at the beginning or sooner whether keys exist or not. Okay? I'm looking for hat, for example. So hat start. You have to decompose this one. Start at H is there. Follow this one, A is there, there is T is there, follow the point, fetch the data. Does it exist? You want to fetch the rest of the data or if the keys exist or not? It depends on what you're planning to do here. Okay? So again, this is the prefix tree, if you know that. So what you have here, we search for the data, we talk about, we have some, properties associated with. The first one, the shape only depends on the key space and the length, okay? So if you try to compare this one with the B plus tree, the B plus tree is not deterministic. This is deterministic. So regardless, if you take a look, regardless you start, if you have hat or hello, hat, have, regardless whether you start, for example, inserting hello, then after that hat or have, or start with have, hello, you're going to have the same structure. It's going to be deterministic. For the B plus tree, it's not deterministic. Why? Because you see, if you start from 1 to 100 in one order, this is going to have like specific structure. Then if it has 150, 60, random number from 1 to 100, so the structure is going to be different. So the order that you're going to perform the insertion is going to be different. At the end, it's going to cause the tree is going to be, at the end, it's going to be different because the number of nodes or the keys that store the, for example, the leave nodes is going to be different. And you are aware of this one. You see that. You're going to double check if you try to use the different size of the nodes or the n value n that you're going to test it in the quiz. You see that maybe end up we have different trees structure at the end. Okay? So it is not deterministic. Here it is deterministic. Okay? So the all operation that you're going to perform here has what's called big OK complexity. So it depends on the search key that you're looking for. The size of the length of the key is not non-predictable. So it's going to be big OK. It depends on the number of keys. For the B plus C, we have big O log n. It's going to be predictable. for all regards whatever the key that you're looking for. You start from the top and you're going to reach the leaf node, then you're going to decide whether the keys exist or not. So here, for example, if I'm looking for hat, it's going to cost me 1, 2, 3. If you're looking for hello, it's going to be 5 because of the size of the key. Okay? Generally speaking, for the try, I guess it's going to be faster for the point query than the B+ tree. If you look for the actual exact value, so it's easy to figure out, find the keys exist or not. And if not, it exists, it's easy to compromise, it's easy to get the key here. And generally speaking, in general, I mean. Okay, so let's take a look. How can we, let's say, implement this one? Okay. So before we talk about this one, I'm going to talk about what do you mean by the span. If you found the terminology span in the tree in general, which that means just represent, I mean, the number of, let's say, the branches that we have, or the children that we have, or outgoing branches, I guess. Yeah, it's better to say that. For example, here with the B+ tree, the fan is going to be n+1. Okay, so you maybe have n up to, let's say, outgoing branch of each node. I'm talking the non-leaf node up to n-1. Oh, sorry, n+1 pointers. Okay. Here, for the try index, we define this one as what? As of the try level, a span of the try level, is the number of bits for a specific level, is the number of bits, okay, that each partial key or digit represents, okay, in each node in each level. So how many bits can you use in order to represent each, let's say, bit in each level here? So this is just a simple example, simple try, which store only 1 bit try. Of course, it's not optimal, it's not a good solution, but just to give you an idea, how can we do this one? So assume that we have a letters, 3 keys, 1, 2, 3, and this is the binary representation, and we have here 16 bits, okay? Just to represent them. So I'm gonna use 1 bit span try. That means for each level, I'm gonna use 1 bit and gonna tell me whether go 0 or 1. This is the option that we have. So because it's gonna only outgoing branch, the span is gonna be outgo to 0 or 1, no more, because I'm gonna use only 1 bit. Okay, if you use 2 bits, that means there 0, 0, 0, 1, 1, 0, 1, 1, etc. If you try to put this one in 1 level. Okay, so in this case, I'm going to do what? I start with the top. So in each level, I can't tell or I can't distinguish between either the value that I'm looking for is going to be 0 or 1. So I start all of them. Remember, we're going to store all of them, okay? So this is the data. So first one is going to be 0. In order to store the 0, so I'm going to have for this level to start here, I'm going to have like, you can see the search key, pointer, the search key, and pointer, because they have a 0 and 1. We can distinguish between 0 and 1. So if the 0, this level, at this position has value, or the search key has value of 0, so that means I'm going to have a pointer to the lower level. If not, I'm going to use a null or empty. Okay? Just to denote that means there is no, branch, or there is no value at this level. Okay? So it looks like you have only space to the 0, it's only to have to represent 0 or 1 distinguish between each level. So start from 0 here, for the second, for the third, you see for the first, and the next level is going to be point to the 0. And here, in the next level here, the next value, let me clear this one here. The next one here, we still have zeros here. Then we're going to repeat this one 10 times. Yeah, 11 times. So we're going to repeat this one 10 times here for this one. The total is going to be 11, all right? Okay, up to here. Okay, so we have 0. Then after that, we have 10 zeros left. So I'm going to repeat this one 10 times. Then here, when you reach this one here, that means I'm here in this point. Now we take a look at the next one. What do you have? We have 0 and we have 1. So we have, for the 0, we are going one direction, and 1 we have another direction. So in this case, for the 0, go this direction. For 1, now finally, go to the pointer to the lower level. So branching will distinguish between 0 and 1. Each of them, they have their value. Go with the 0 of this 0 part. You have 1, 0, 1, 0. So this one is going to be 1. I have a pointer to the 1. 0 is going to be a pointer. 0 is going to have a value, 1 not. Then after that, we have a 1. Then after that, I'm done. Then here at the end, you have like a pointer to the last level. For the last 0, it's not going to be a pointer to the child. It's going to be the last pointer. So if you keep tracking or starting from the top and to the bottom, you are going to construct the key that you're looking for, or the value that you're looking for. Okay? For the rest here, I think they'll be the same here. I'm not going to give you just one example here. We have 1. Then after that we have, let's say 1. Then after that we have 0, 1. So we have a 1 here. Then for the 1 we have the 0 has a value. Then after that we have 1. Because both value of the search key is going to be, out branching or going into 2 branches. And continue doing this one. So the red one is going to be pointed to the tuple, the actual tuple here, and it looks like this is the leaf node that we have, and the rest is going to be the pointer to what's called, the next or child on the next level. Okay, this is how to implement, how it looks like on the side. Okay, we can do some optimization. So someone will say, why you need to specify 0, 1 as long as I know that's 0, 1? Yeah, so why you need to reserve a space for the 0 and 1? So there is no need to have spaces. The only thing I need to reserve the pointers. You can say, for example, the first one is going to be pointer to the 0, and the second one, if there's going to be pointer, if in this level the 1 has a value, or it's going to be a core, and then the search key, right? So that's what we're doing here. So this one exactly what we did here, and the simple thing here, I just remove this. So this one is not going to be part of the result. Okay, for this. So that's what it looks like. Okay. If we notice something here, now we're going to modify something here, okay? If we notice that, okay, for, let's say, when a branch, there is no other key can match this. So if you take a look here, in this place, it looks like I'm still talking about the K10, yeah? Did you see K5 or K10, 2025? No. Starting with this point here, I know for sure this one, there is no other keys can be a match here. Only one key, based on the data that we have. And here in this branch, if you take this point here and here, you see that in the block, there's no other key than K25. And this is only match exact one key, which in this case, K31, which there is no other key. Okay? So in this case, do we need to store this one? No. We don't need to store it. We can, only store the pointer to the tuple where the data, we can what's called compress the data in this case. So that's what we have. So we can compress this one, since in this point, I don't have any other option. No other key can be matched except the K, let's say 10, and the other 25 and 31. So remove that part, compress this one, add pointer at this point, because here you can't tell exactly. At this point here, you can't tell. If you reach 0 here, this means definitely that's K10. Here, if you reach 0 here, definitely it's the K25, and here each one, that means definitely it's K31, and that's what we did. And this is what you call the Radix tree, which is like omit all the nodes with only a single child, which is what's called the Radix tree, which is like a special a specialization of tri index, or tree in this case. So the same structure, the same thing, but we are going to omit all the nodes with the single child. Okay. So there is no way. We'll try to take a look at the insertion, deletion, etc. There is no standard way for every single. We can generalize that. Okay, it depends on the implementation. For the B+ tree, it looks like we have a clear implementation. We have a clear procedure, steps we need to follow when we perform insertion and deletion. Here, no. It depends on the implementation. Okay, just to give you an idea what's going on. How can you perform? Let's say insertion and deletion. Assume that you want to insert this information. Let's say and delete. Then after that, delete hat and her. One thing, by the way, here you see that by omitting that, I think I missed that part, but it's going to be similar here. So here, if you take a look here, so it looks like you have here, you can have like a node here. Assume it's going to be like, if I think, what's the first one? Is hello? Hello, yeah? Yeah. So this one I can say H. I don't know, I didn't remember the rest. We'll say, assume that if you take a look at the hello and etc. So somehow you have pointer here, and you can HE and OM, and let's say XY and etc. So assume the data AHE, AOM, and AXY. Okay, this is the way how to represent the data. So since I'm gonna omit all the nodes with only a single child, so maybe in this case you're gonna have what? Maybe have like multiple, let's say value can be stored in the same node here for simplest. So something like this. Okay, so hello, and here jump H, hello, go this one, hat, go this direction, have is gonna be go this direction. Okay, So anyway, if you try to insert here, so H, A, and here you need to do what? I can't insert this one, but here I can do this one what? I can do I and R and a pointer where the data can be stored in the disk. That's one thing here. If you want to delete this one, let me back here. Yeah, for the people, I mean, the Radix looks like, as forget to mention that, the nodes are going to be what? It's going to be represent, I mean, the largest prefix before the key is going to be different. So in order to help us, in order to have less numbers. So that's why here, the largest numbers is because you remember, it's the same thing with the key, said, I think, 25 or 31, etc. So in this case, you know if exactly the search key is going to be, for example, hello. If you try to apply this for the here. Yeah. So in this case, since I know in this case, there is no more other key match. And here, since we have two, so this one can be represented like this. This is a try. This is how it's going to be in the Radix. It's going to be H. Then H is going to be have a pointer to the lower level here. You can only one. So it's going to be H, A. And here, let's say L, 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 O, because all of them here can be combined in one key. Yeah? Remember that we can compress that. So it's going to be like this. And here, since we have A, still have T and V here, okay? So it's going to be T and V here, E. I compress this one here, and this one, if you have something, I can compress this one here. So that's Radix. I forgot to mention this one, but that's what we did when we compress, I mean, the, since there's no other key that match in this subtree tree, so you can compress them. In other words, you can represent the large, to say, prefix before the key different. And that's what we did here. Clear? So we are here. So now when you try to delete something, let's try to delete something here. I want to delete, let's say, hat. So hat, H-A-T. I cannot delete A here from here. If you delete A, that means I'm going to lose access here to the rest of the data. So all the thing I need to do is just to search the data and delete this, and with the pointer. And the same thing for the have a VE, you can delete the whole thing. And now it depends. Either we're going to consolidate the space, since they'll have only one key, can be matched here, so I'm going to compress this one. Or represent consolidate that, and going to be what? These nodes are going to be consolidated in order to represent only, I want to say, the largest prefix before the key is going to be branching. So in this case, it's going to be here. Instead, we have the data, it's going to be A-I-R. Instead, you have all this information. And that's what we have here. As one thing here, actually, that's what we're going to have. Okay? So another thing, I mean, just an idea to see there's a different way. I think, I'm sure, I thought that you studied this one in data structure somehow. And as a prefix tree, we use this one to perform the search, organize the data, speed up the access to the data. Yeah. Another thing you need to take a look here, if you compare this kind of query that, or the index that we have, we cannot guarantee all these indexes are going to work with every single possible, say, query that we have. Let me give you an example here. If you try to find all the customer, whatever zip code or between value, give you point query or range query, you see that I'm not going to say every single range query allow you to use the B+ tree in an efficient way. Not all of them. So for example, if I said, find all the Wikipedia articles that contains, for example, the word database. You're looking for the data that's going to store, to say, information about the documents, textbook or whatever. Then you're looking for specific word, or the document that contains specific word, and the beginning, in the middle, and the end, and etc. So the question here: how can we make such an index that allow me, before what's called the keyword search? Okay, give me your example. Give you an example here first. Remember this, the Wikipedia example that we have? So we said we have the user account, so that contains information about the user that has an account, to say, on the Wikipedia. Here we have a number of pages, and for each page is going to have like a different revision, which is going to be written by users. Okay? Here in this revision, there is a content. I'm trying to search within this content. Okay? Keyword search. So in this case, someone is going to say, okay, I'm going to create an index, okay, on the content attribute. Can you do this one here? Let's think about this one. I have a table, I create an index based on the content. Then now, I'm gonna perform this kind of query. Do you think this query can use this or not? Can use this index or not? Based on your experience. Regardless, whatever you have. If you write this query like this, and you have built an index based on the P+3, whatever index, based on the content, based on text. Okay, then you're gonna perform like index like, a query like this. And you said, for example, I'm use a wildcard, okay, at the beginning and the end. And I said, does this one, or this query, is going to use this index or not? Of course, the answer is not. But why? Just to provide you with how the people, obviously, the Postgres is gonna work with the data in general. Okay, so assume, let me give me a second here. I need to go to the whiteboard and go over this one again. Assume that you have a P+3 index based on, let's say, a name. Okay, you build this one based on a name, or let's say department. Okay, whatever, text, char, etc. Okay, then now using this one, you know that the P+3 index can be used, for any attribute comparison in general. If you have greater than, less than, not equal, equal, and etc., and between, and etc., range require, etc. And also, the index can be used for like, like, yeah? You can use like in order to search, but not every single like, yeah? So one of them, if the argument of the like is constant, or this is the most of the database management system, okay? If the argument that you're gonna perform, let's give you the example, select, and those are more clear to say whatever star from the relation R, I build the index for the based on that relation R, based on the department name. Okay, where let's use name. It's easy just to write name like I'm trying to say. Okay, like you say computer science. Okay, or the name contains computer science. At least the first two letters are C, S, and the rest I'm not sure. Or let's see, the department will start with S, but I'm not sure with the rest. Okay, C, and here you know that you can use wildcard, okay, or the pattern, regular expression. You know that. Okay, so in this case, or is going to equal or like is equal to specific value is going to be constant. Okay, so in this case, the system going to say, okay, if you have name like something, okay, definitely I can use the P+3 index here. If this one, the first letter is not wildcard, so yes, I can use the P+3. But let's write this one different color. If you need to have the query here where the name, let's say, I'm trying to use like, I'm not sure. It contains C, but it's not at the beginning, somewhere, substring. Wildcard, C, another wildcard, etc. So this one, no, I can't use the P+3 because the condition here must be either constant or this, whatever string that you try to look for, doesn't start with the wildcard character. This is a condition that we have here. So here in this case, if you said name like, I'm talking, that means they are not going to use the P+3. It works, but it's not going to work. It's going to perform sequential scan in this case. Like, let's say, Y. And the Y is another, let's say, name like last name. So this attribute is attribute. Here, at least the MySQL is not allow you to do that. And the most of the database management system. If this one starts with a wildcard, or if this one is not compared with non-constant value. This is not constant. This is another attribute. So in this case, both of them, we are not enabled to use the index. So now I have a problem. I'm trying to search with them to say a content of the document, but I do have index based on the content, but I cannot use the index because when you search, perform the keyword search, I'm definitely somehow I'm going to use the wildcard at the beginning because I'm looking for the document that contains this value. Okay, database. At the beginning, in the middle, at the end, and etc. So using the traditional way that we build index is not going to work. So how can you solve that? We're going to solve this one using the inverted index. Okay? I'm not sure whether you're familiar, we have two different types of index. One of them we call this one inverted. The other one is like a forward index. Generally speaking, I think there's a data mining class do we have here, or the information retrieval class in the IIT. Somehow we do have a course. This course is going to cover this one in more details. Generally speaking, when you build index about the document, we're going to create what is called the forward index. So you have a list mapping the list of document to the list or the, let's say, a document into a set of keywords that's stored within this document. So in this case, you can see that we have D1, D2, D3, 3 documents, and each document is going to have a word 1, word 2, word 5, word 6, and word 2, and etc. So this is what we call forward index, mapping from document to a set of words. Inverted index is going to be reverse order. It's going to be mapping from what? From the set or the keyword into a set of, let's say, documents. That's why they call this one inverted index. So how can you solve this one? How can you build this one? Because this B plus 3 is not helping. So I'm going to do what? This is a simple solution. Naive solution is not good. First of all, find out all the keywords that you can extract from all the data that we have, or the documents that we have, or the content, or the different page revisions that we have in our data. Then make table with one Boolean attribute for each keyword. For example, assume that we have 1, 2, 3, 4, 5 keywords. For example, computer, printer, laptop, and desk. Those are the list of keywords that we extract from the data. Okay? Then I'm gonna do what? I'm gonna create a table which is gonna have a Boolean attribute for each attribute here. And that this table is gonna have like an entry or one tuple per document, or per, let's say, page if we have. Okay? So for the first document here, it's gonna be here. Since we have, for example, 4 attributes, and those are gonna be has like a value true or false. It depends whether this word exists in this document or not. So for the first document here, we can say the computer is true. They have computer, and they have this document contains printer, and the rest is gonna be false because we don't have, for example, laptop or desk within this document. And continue doing that. Then after that, at the top of this table, we're gonna build like an index for all the attributes that including only true pointer. It's gonna pointer to what? To the tuples that where the value of this index or this keyword is going to be evaluated to the true or has true. For example, this computer index is going to have only pointer to the document that contains computer as a word. So here it's going to be only point to the first tuple. Yeah, this printer index is going to have a pointer to all the tuples. They're going to have what? The printer as let's say keyword. So this one is going to have the first, and it's going to be point. Let's be clear. This one's going to be clear to see it. So it's going to be the first here and the second, and etc. Of course, it's not a good solution to do that. So how can you build this one? I'm gonna create an invert index in a more efficient way. So in this case, we're gonna have like create an index or inverted index against this inverted mapping from what? From the word to the document. Okay, or the tuple that contains whatever set of attribute target attributes. This is a simple solution. Our structure, you can imagine how it looks like. We have like, remember that we did this one before with the secondary index when we use a bucket. The same thing, the structure we're going to use here. So you have a list of the keyword that we have, and you have a pointer to what? To the bucket, where the beginning of the bucket has the list of all the pointer to the tuple or the document that contains this search key on there. Okay? So the first one, pointer to the document that contains the pointer. Here the desk, since we have two, we're going to include 2 pointers in the bucket, which is going to be pointed to the document that contains the desk, and etc. So that's what you'd like to do. This is the structure of what is called the inverted index. You're going to notice later when you work with a keyword search, I'm not looking for whether the, let's say, specific keywords exist or not. I'm looking for more information. Mainly we're going to say, for example, tell me, for example, the document that contains the search key or the keyword, for example, computer, at least 5 times. Or the number of accounts with the document that contains, let's say, the search key, A and B, and between of them, maybe the difference between them, maybe 5 or 6 characters. Okay? Find the document that contains cat and dog, and the difference, or phrase, and the difference between cat and dog words, maybe have 5 or 6 words in between. Okay, or find the document that contains, let's say, a search key or specific search key entitled that equals specific value. Yeah, so it looks like we can expand this one. We add more information onto the store here in order to reflect the change that we're looking for. Okay, so this is another example. As you mentioned, I think information retrieval. I think we do have a class. I don't recall the exact name of this class, But I believe either going to be data mining class or information retrieval class. It's going to cover this one more details, different ways. How can we extract the search key that we come up with? Because we cannot elaborate of a possible search key because the size of the index is going to be too large, and etc. So we have a document here. The cat is whatever, was raining, cat, dog, etc. Okay? Then here you can build an index, and invert an index. You're going to have the search key or the set of keywords going to be mapping to the document that contains them. Generally speaking, when you work with inverted index, okay, this one will allow us in order to do different types of queries that we cannot perform using B plus tree. The first one, the phrase search. So in this case, I'm going to give you, like, for example, I'm looking for or ask the query that please give me or locate, let's say, the tuples or the records or the document that contains a list of words in the given order. So that means must contain cat, then dog, or let's say A, then B, then C, then D. Okay, in the same order. That's one thing. Also, allow us to perform what's called proximity, search. This means find the tuple or the document, whatever, where the two words occur within inwards of each other. For example, I'm looking for the cat and dog, and the difference between them maybe 5, 6, 7, 8, 10 words in between of them. Of course, we cannot answer this query using the B plus tree. That's why now we need to use the inverted index in order to allow us to answer this query. The third one was the wildcard character or search. In this case, remember when we said the B plus tree is not allowed you to use the like if the first, or they say the search key is the first letter is going to contain wildcard and not constant. Okay? For example, I think attribute like another attribute, you cannot use the B plus tree. So they have to use the inverted index in this case. So this is going to give me any regular expression, anyone, in order, or to say any regular expression, used as a pattern in order to tell me, in order to specify what I'm looking for. Those are just an examples. By the way, you notice that I speak faster, okay? Because generally speaking, we have a lot of slides to cover in this chapter, and mainly it's not gonna be part of the exam. Oh, I made a mistake. Now everyone is gonna disconnect and say, oh, so it's not interesting. It's good to know, okay? But it's not gonna be part of the exam. That's why I'm gonna just, speed up when you cover them, okay? So this, a set of kind of queries or some examples. You say, for example, find the article document with a cat and dog, okay, with a cat or dog, with a cat is not dog and not dog, cat in the title, cat and dog within 5 words in between of them, okay, or maybe that cat that appears 5 times at least. The dog that contains cat 5 times or 6 times or 100 times appears in the document, something like this, okay. So when you design, or let's say, when you develop inverted index in general, there's 2 primary decisions we need to decide. Okay, the first one, what kind of information I need to store? Because now, in order to answer this query here, it looks like it's not enough we have like a cat, then here directly it's gonna be, let's say, pointed to the bucket, then this one is gonna be list of pointer that point the document that contains the cat. Here, I'm not interested only in the search key. Only I need to have like extra metadata. I need to add extra information in order to tell me or decide, for example, whether the cat is the title or not, whether it's going to be this search key or this exact keyword exists, let's say, the title or the abstract or the conclusion or whatever. Yeah, and how can you decide how many this document contains, this how frequent this word appears in this document? So it looks like here you need to decide what kind of information. It looks like we need to add extra information in order to help me in order to answer this query. Okay? So maybe in general, we say additional information, maybe it's going to be word frequency, position, where is the exact position, and maybe other metadata. So that's what we decide. When you update, of course, not every time modify the document, you need to update the index. It's better to do what? Delay the update of the index later, because if every time you're going to perform the index, you need to update the index. It's not only single entry. We have a lot of information you need to update, large amount of, let's say, metadata. Of course, it depends what kind of information you need to store in the index. One example in order to go over this one to see the inverted index. Take a look to the generalized inverted index in the Postgres. If you click over this one, trust me, you trust me, yeah? So you can click whatever link I give it to you. Anyway, So if you go there, it's going to give you some details or more details about the inverted index. It's worth to take a look to see. Or it depends whatever database management system you like to use or you currently use, your favorite one. Take a look at how they work with the inverted index. How can you use this one? How can you, when you create the index, tell I want this kind of index to be inverted index. Then after that, do some examples or some practice in order to use them. This is just an example how do we just imagine what the counter or the extra metadata that we need to store in the index in order to help me in order to answer this kind of query. The type, for example, where this information can be stored, either can be in the title, say in the author, in the abstract, the exact position. That means this word can be, you can say, for example, the document 1, or let's say in the position 1.5, for example, the line of the 5th word in the document. Maybe you can say if this one appears multiple times, the times maybe in the 5th, as the 5th word, and the 10th and 15th, you can add this information here. In the author, for example, it appears multiple times here, and here you can give more details about, the pointer to the data, and maybe you can add how frequent this one appears in the doc, or maybe you can drag this information. Okay? So now we're going to talk about something different here. So far, we talk about different types of index. Mainly, we talk about the conventional index in general. Then after that, we talk about the B+3 and the hash index. Okay, and to give you an idea about what you call, the inverted index. All of them, or the common properties that you have, all the indexes we talk about, we have the search key value. This value can be taken from one-dimensional space or set. Even if it composite attribute. Okay. It looks like you have, the index is going to be based on single dimension. Assume that we have attribute A or B or ID or student ID or name or etc. So if you have a composite attribute, try to build this one, you're going to see that it's not efficient in order to answer a query that what you call multi-dimensional, pattern. So here, if you build an index, and you try to build the index with the ID, or let's say name, so you have only one way in order to store the database, only the name here. That's what you call one-dimensional space. Even we have a composite attribute based A and B, so in this case, we're going to store the database one based on A, then after that, based on the B. So we cannot store them based on A and B. In other words, even if you have a composite attribute, this one does not allow you to do what? Related information, or the information that's close to each other, it's gonna be stored in the same, or let's say, next to each other in the database. Remember, you have a relational table. Well, after that, you need to store the data on the disk in the blocks. And the goal from the first day in this class to do what? Try to reduce the number of disk input out operation in order to retrieve the data. So building and say composite attributes or index based on the composite attributes is not going to achieve this goal. Make sure that, for example, assume that we have A and B. Okay. Assume A is going to be H and B is going to be salary. Okay. So when you build this index here, what I wish to do, I have the information that's stored in this place. I wish it's going to be stored in the same bucket or next to each other. It's easy for me to access the data. Then the next one is going to be stored to each other. Okay, close to each other, or the related information can be stored in the same bucket if it's possible. In order to, once you get access this block, allow me to answer the query that related to the age, for example, less than 50, and the salary less than or within the say 100K, something like this. So composite attribute, I cannot do this one because either going to be stored the value H and P. Okay, that's one thing. And the order of the data that if you store the data, it's going to be based on what? Based on the age or based on the salary, etc. Because we cannot store the data based on two attributes at the same time. Because either it's going to be this direction or this direction. Because you have only one way, in other words, to lay out the data on the disk. More is going to be more clear later. We talk about the multi-dimensional index. So as a solution of this one, we use, or I show you multiple index or key index. So since we have multiple keys, I'm going to do what? I'm not going to do the composite attribute, but I'm going to do what? I build index based on, say, different attributes. For example, for the first level, it's going to be based on attribute 1. For the second level, it's going to be based on attribute 2. But this one is not going to help me in order to answer the query in a more efficient way. It depends. If I give you, for example, the information or the where class, I give you like the search key based on the first level, or the attribute here to use and build the index in the first level. So this one is going to be more efficient because you have the value, for example, for A equals something. So if you give you A equals something, so you build the index based on A, then after that you build the index based on B, and B equal another value, so it's easy to start from A. Then after that you're going to reduce the number of disk input output operation, because based on the value of A, it's going to either go in one direction, either this one or this one or this one. Yeah. If they give you A equal 10, so you can answer the query here only in this case. Yeah. If I said, for example, here I give you B equals something, so I don't give you the first level of the value that you use in the first level in the index, I give you the second level value. So in this case, it's going to require for me to access too many disk input output operations. So remember, any index, it might be most of them give me, allow me to answer the query, but I'm looking for the one that's going to be more efficient. The one that is not going to end up having what's called sequential scan. Okay? Must, outperform the sequential scan. Okay? So now we take a look to different other approach, different way in order to build this index. Okay? I'm not going to be the B plus C and the hash table or the multiple key index, although this one going to be, you can use this one as tree-like structure. But we're going to show you that there is another tree structure, like structure, we said like, because not the exact tree. It's going to help us in order to answer this query or build the index in multi-dimensional. Okay, so we're going to take a look to the tree-like structure and the hash-like structure. It's not the exact hashing, because we're going to use the hash in different way. Then after that, we talk about the bitmap. Okay, why we need, in other words, multi-dimensional index. Why I cannot use B plus 3 and whatever hash index in order to answer any query. Why there is a need what's it called the multi-dimensional index. There is many applications that require us to see the data in 2 or more dimensions. Okay, geographical information system, you're familiar with this one. Or let's take a look what is called the spatial database. You're familiar with the database, spatial database. With the database is going to be what? It's going to allow us in order to query the data that can be represented as an object. Now it looks like we have a different way in order to represent the data. I can represent the data as an object, which is going to be defined as, say, in geometric space. What do you mean the object? Allow me to say, for example, represent the object as points, lines, polygons, rectangle, and etc. Yeah. So assume that you give you the data that have x and y. Okay, x coordinate and y coordinate, which have the points here. Then I ask you, for example, could you find, for example, the closest restaurant to my location? Something like this. We can answer that question or this query using the B plus tree, but it's going to be expensive. Actually, the sequential scan is going to be much faster in this case. Why? Because the way that the data is going to be stored here or sorted in the blocks, the related data here, we cannot guarantee that the data or the related data or the information that close each other for the x, y values is going to be stored in the one block. Yeah. So either here, if you have, let's say, the simple way, if you try to build the B plus tree, I'm going to build one tree for the value index for x and another one for y. Then I'm going to consult this and this in order to answer the query, which is not an efficient way. Even for the composite attribute is not going to help me. Anyway, so it looks like we do have like some application requires data in the 2 or more dimensions. Why? Because, for example, you have images and structure, you can allow you to store the data, especially the data that contains a lot of information, and mainly just I want to perform an analytical queries, just to extract some knowledge, some information, get some insight from the data. Okay? You can talk, I think you're familiar with the content-based retrieval. So this looks like I'm talking about the information retrieval class, but here I'm just mainly focused about how can we use index in order to help me in order to, let's say, work with the spatial data in general, or the geometric information data. Okay? So here, multi-dimensional index is combined several dimensions into one index. So in this case, we are going to build one index in the way that all the related information that goes in multiple multi-dimensional, for example, 2, 3, 4, 6, 8, whatever. If you can use a vector or tensor vector, you're going to see that you have multiple dimensions, 3, 4, 5, 6. So it's easy to organize the data and easy to acquire the data and extract the information that you're looking for. Again, this is not part of the exam. I'm not going to ask you about that, but just to give you an idea about that, we have different types of index and how can we use them. Okay? So here in this case, in this index, so data is going to be what here? It might be looking for a point. So you have a different types to query here, actually here. We're interesting that with different types of queries. Not, I mean, I'm looking for exact point, etc. So I'm looking, for example, range query or nearest neighbor query or spatial, let's say, a query. We're going to talk about this one in more details. Anyway, here you can represent the data as point. When point, that means you have A1 and B1, that means 1 point. You can represent data as a line. So I can say from A1 and B2 up to B3. So this is the line that I'm looking for. Or you can represent the data as a polygon or say whatever, I mean a rectangle or a triangle, whatever, I mean dimension that we're going to use in order to represent the data that's stored in this area here. You can see for A2, A3, A4, they say give 1 dimension and they say B4 and B5. Okay, so we're going to see how can we build this index which allow me, it looks like it can be represented as a map in general, which allow me to answer different types of query. Okay, and also we can add more comparison here. It's not gonna say, for example, less than or greater than or not equal. I can use, for example, whether I can say whether one object contains another object or not. Whether one object is gonna be, let's say, overlapping with another object or not. So you see that there's different types of query you can ask, you can perform. Okay. So as I mentioned, multidimensional index information is going to be mainly a spatial database. And when you talk about the spatial database, we can say we have 2 different types actually here. You can say this is like an application, one of them geographic information system, and also computer-aided graphs or design manufacturing that we use, spatial database in this case. So the data is not only 1 dimension, it can be 2, 3, 4, 5, 6 dimensions. We can separate or distinguish between 2 different, let's say, type of multi-dimensional index. One of them we call this one the low dimensional index, and the other one we call this one the high dimensional index. When we say low, this means, generally speaking, we have from 2 up to 4. So it looks like when I say 2 dimensional, that means we will have x and y. 3 dimension x, y, z. You can represent the 3 dimension. 4 dimension x, y, z, d. Okay, and the high dimension that means something maybe. Mainly, actually, when you talk about, let's say, images or video objects, etc., can be represented at more than dimensions. Okay, I think 60, 64, maybe up to 500 dimensions. You can use this one. I think tensor, vector tensors, if you remember this one, they use this one. I'm not sure. I think at least 3 or 4 you can have multiple dimensions, which allow you in order to represent the data more efficient way, extract the meaningful information in this case. Anyway. So the data can be stored as an object, and now an object might be house, might be pipeline, might be point of interest, for example, locations and whatever data that you want to represent. Then you can use this multidimensional index in order to help you in order to answer this query. We talk about this one, spatial data. Now, as I mentioned here, we do have like for the application with the spatial data in general, typical queries are concerned with a spatial proximity. Okay, we have a different types of query. One of them, partial match query. The second one, range query. It's not the exact one they're looking for. Here's different. I'm looking about the object. Nearest neighbor queries and where am I queries. Okay, so let's take a look. Assume the data going to be represented like this. Okay, as a map. Then now I said, give you like find all the points or the object that intersect with the y equal 50. So here I'm building my data based on x and y. Let's say 2 dimensions, x and y. Okay? Now in the partial match query, either gonna be give you the value of x or the value of y. If you give me both of them, that's perfect. But I'm talking about the partial query. This allow you to answer or give you at least one, let's say, value that corresponded to 1 dimension of the index. Then you need to use so this kind of queries allow using this index what's called the partial match query. Okay, so find all the points that intersect with the y equal 50. So in this case, you can give me the house. Okay, or maybe you have a map, then you need to go with a specific direction. I want to see what I can see in the front of me, or give you like specific x and y. You can have an x and y coordinates. In this case, you can specify what exactly located at that location of that point. So far, so good, guys. The nearest neighbor query. I give you what? I give you like a set of points that be represented in 2 dimensions or more. Assume that for simplicity you have 2 dimensions, x and y. Then I give you like, give me the nearest object that satisfies the given condition. For example, I'm here at this point. Give me, assume that you are this location, and those are the list of the restaurants that are around you. Then I say, I'm looking for the restaurant that the nearest, you say, restaurant, or the closest restaurant to my location. So in this case, I'm going to say, maybe you're going to say this one. Okay? Of course, it depends on if you move, keep moving here, so the data is going to be moved. So we need to find an efficient way in order to answer this query. I'm keeping but you can put 100 lines under the efficient way. Okay? Where am I? One interesting query. Give you what? In this case, it's going to give you, or ask you about what? Your location. For example, give me a list of the object that contains this location. Right now, if I ask you where you are, you're going to say, okay, you're in your room, or you're outside, or myself, maybe I'm stuck in my office, in my building, in this location, in this area, etc. So you can answer this query. Okay? Of course, this interesting thing here, how can we represent the data? This is the question here. How can I represent the data in the way that, and build an index in the way that can allow me to answer the set of query that I showed to you in a more efficient way. Okay? I skipped one query. We call this one the range query here. The range query, of course, between two values, but I'm going to give you, like, let's say, on a block or area. I said, okay, give me what kind of objects are located in this area. That's what's called the range query here. So give me just the list of the objects that located partially or entirely or completely within this object, or within, let's say, certain range. I give you like x and y condition. Of course, in this case, I don't know exactly what the value of x. Maybe it's going to be 60 up to 99, and the y is going to be, for example, between 50 and 70. So give you the range in the area, and give me, or tell me what the kind of object that's located in this area. If you try to answer this query using the P+3, is not going to be an efficient way to perform that. I skipped this part. Generally speaking, we can go over this one more details later if you're interested. But in this case, if you try to build an index using P+3 and try to perform the sequential scan, most of the situation you end up that the sequential scan is going to outperform the P+3. That means there is no way to use the traditional index in order to answer this query. That means there is a need in order to have, like, let's say, multi-dimensional index in order to help me in order to answer this query a more efficient way. Okay? Okay. So the reason behind this one, as I mentioned before, we need to make sure that geographically related data must be stored in the same data block, or in the next, or the neighbor, or next to each other. It's not going to be spread everywhere. In other words, if we try to see, go back here. If you're interested to know what's going on in this area, okay? So if you have this dimension here, assume that we have a blocks of data stored like this. Okay? If you manage to store this information that in the index in one block, and this one in another block, or the same block, and this one the same block, the same block, the same block, the same block, if you fetch all these 6 blocks, then you're going to will give you the result that you're looking for in a more efficient way. But if you store this information, this block, that, in this area, in different blocks, that means in order to achieve all the information here, requires me maybe perform too many random discounted order operations, which is going to be costly operation, which is the one that we try to avoid here. Okay? That's the main reason why we cannot use the normal index. As I mentioned here, we do have like a different types of different data structure we can use in order to use the index or build this index. I'm going to go over only 3 of them. I'm not going to go more details, but give you an idea. Then I'm going to give you like some links, for example, if you want to learn more, or how can you use them in using Postgres, was the main thing that we're going to cover here. If you're interested to learn about more, you can double check, for example, take a look to the manual for your favorite database management system in order to see how can we use them. It's interesting, by the way, especially if you work with a large amount of data. And just mainly you're going to extract information, meaningful information. And remember, speed, performance, that we're looking for. So we can come up with another definition for the multi-dimensional index as what? As an index or multi-dimensional data. So data is going to be multi-dimensional in this case. That helps us in order to answer what is called the multi-dimensional queries that I talk about in a more efficient way. Which when I say we have like a range query, nearest neighbor query, and a spatial and say where am I query. Okay? So we're gonna have 2 different types of data structure. I'm not gonna go over more details. I'm gonna for what's called the table-based or hash-like structure, the grid index file. And the second type of data structure that we can cover here, which is called the tree-like or the tree-based structure. So it looks like they didn't be in the tree, but a different way. The kind of information that can be stored there is different. So we're gonna just go over the KG tree and the R tree in more details, at least in order to make sure that we understand what's going on. Here, one interesting thing when you talk about the table-based or to say hash-like structure, when you talk about the hash, it doesn't mean we're going to use the hash in the normal way that we know about the hash table. You know the hash, when you use the build an index based on the hash index, you need to do what? You need to use the hash function, compute the hash function based on the specific attribute or search key, produce the hash value, then the hash value is going to tell you exactly where, let's say, the bucket that you want, you're going to use in order to store this element or the search key. Here, when you say the hashing, I'm going to say, actually, I'm not going to say hash, but it's going to do what? When you compute the hash value, this hash value somehow is not hashing value, is not hash function, but it looks like just to locate or to say, direct me to the actual bucket where the data is going to be stored, but it's not going to be hash value. So I'm not going to use, for example, modules, something in order to compute that. It's going to be more details later. Partition hash function, by the way, in this case, we assume that we have x and y. Okay? Now we need to build the index based on the x and y. Let's say what you call, the multidimensional index. Okay? So in this case, for x, I'm going to use one hash value. Let's say hash function, let's say x modules, let's say h1 in order to compute x, and they use another hash value, different hash value in order to compute y. The value or hash value that produced by h is going to be concatenated, or by h1, going to be concatenated with the hash value that produced by h2. Then I can do what in this case? Remember, we need to build or come up with the index that help me in order to answer what's called multidimensional queries in a more efficient way. Partial index, for example, if you try to answer this one, if they give you the value of x and y, assume they give you the value of x. Use h1 over the x, produce whatever the value of, let's say, xi, or let's say z, okay? I don't have the value of y, but I'm still being able to what? To compute this part, yeah? Then I can use whatever information I have in order to navigate or look up in the hash index that I have. In the previous hash index that we have, you have to give me the exact key. If you compute or build the index based on composite hash value or the search key, so in this case, you have to compute x, you need the value of x and the value of y, both of them in order to compute, let's say, correct hash value. Here, there is no need with the partition. Okay, I'm not gonna cover this one, but keep in your mind that looks like we have different hash value. It depends on how our various hash value can be used. And each dimension is going to be contribute to the bucket number or the bucket value by using the corresponding hash value associated or located for this index. Anyway, so let's take a look at the grid index. And the data is going to be what? Partition into space with the grid. Assume we have a value x and y. Let's use age and let's say salary. I want to build multi-dimensional based in 2 dimensions. So here you're going to see, this is my, the data can be stored in the whole area, okay? You can partition the data based on the age, for example, 50, 70, this is 100. Assume the age from 0 to 100. So we'll partition the data based 3 value, from 50 and 70. And the last one could be 100. So in this case, all the ages or points here is going to represent what? The age is that less than or equal 50. Less than 50, sorry. And here it's going to be greater than 50 and what? Less than 70, yeah? And the age is going to be here greater than or equal 70 in this area. In the salary here, you can use different dimension or different values. You can use grid lines in order to partition the space into stripes, okay? Each have a different location or different, let's say, region. So assume that one line here and another line, there is no need to have the same, let's say, value used in order to say divide the data into or the space onto partition based on the salary. Maybe I'm going to use a 3, for example, or 4. Here, let's say less than 50,000, and this is, for example, 70,000. Here, 99,000, and this will be up to 200,000, for example. Okay, so in this case, it's going to be what? The value is going to be for the age less than 50, and the salary is going to be less than 50K. Right? The nice thing, if you build this one, this information that contains all the salary less than, or the list of the people that have salary less than 50,000 and the age less than 50, it's going to be stored in one block. That's the nice thing. So if you try to look for the information, so it looks like related information close to each other in the graph, or let's say in the diagram, or the, let's say, into the space that we have, they'll be stored next to each other. You get the idea? So here, if you try to search, I'm gonna do hashing. So I'm gonna hash the, let's say, the age and the salary. You give me the value of age and salary. Based on the age and salary, I'm gonna do what? This one gonna use in order to locate which bucket I need to go. Whether I'm gonna be located, for example, if age, for example, 70 and the salary 100. Okay. So in this case, I'm gonna say follow here 70. It's gonna be this area greater than or equal 70. Yes, this one. And they say what? The salary is gonna be 100K. So 100K is gonna be located in this area. So here you need just to. This is the bucket that I need to follow. I need to fetch. You see that using this index, I'm being able to what? Efficiently locate the bucket. I don't need to spend or perform sequential scan in order to access the data, but based on the index, just give me what you're looking for and can get the information that you're looking for or find out. Okay? So that's the grid index in general. So you have maybe two different keys. So generally speaking, we have like regions. We call this one regions here, region. And this is gonna can be represented as a bucket. And inside of them, I'm not gonna store the data here. I modify a little bit, okay? I'm gonna here, this is a bucket, and the bucket gonna contain the pointer to the block where the data that satisfies this condition must be located in this bucket gonna be stored. Okay, so this is a region, or we call this one bucket. And the bucket is gonna have a pointer to what? To the block. Okay? And the block it might have what you call overflow. If the block is gonna be full, then you can store the next information, the next and etc. Okay, this is the grid index file. Here's just an example, give you two dimensions. Dimensional, you can have a 3-dimensional, 4-dimensional, etc. But this is just an example here. So again, related data, or sometimes you call this one geographically. That means the data that close each other, that has the meaning close to each other, is going to be stored in the same bucket. That's what we're looking for. The bucket is going to have a pointer to the blocks, and the blocks can have maybe to the main block that contains information that's stored in this bucket or located in this bucket, and you can use overflow. Here we have just different ways in order to represent the data that will be stored here. Okay. By the way, the grid or the file or the lines that we use, or grid lines here, there is no need, for example, to say they must be equal. For example, maybe you can use 5 values in order to just say split or represent the data in Q2, and maybe you use only 1 value or 2 values or 100 values in order to represent the data in the other dimension. So and also when you try to perform insertion, deletion, now you maybe introduce a new line, grid line, or maybe you're gonna do what? You're gonna merge new lines or two grid lines together. It depends on the size of bucket that we have. For example, if we notice that all the data here we have too many or too much overflow, or a lot of overflow blocks is going to be introduced in this, let's say, bucket. So it looks like it's better, in order to have a better performance, split this one into 2 buckets. You see that? You can reduce the size, introduce another grid line, which allow you in order to reduce the number of this compute out operation you're going to perform in order to access the data that can be stored here. We are not going to cover, how can we, insertion, deletion, etc. But just to give you an idea, the structure, the data is going to be in the space, it's going to be based on the grid lines. In the 2 dimensions, for each dimension, you can specify what is the value I need to use in order to, let's say, specify or to say decide with the membership for each bucket. Okay, so just speaking here, the way that you're gonna store the data is gonna be as following. You have to tell me how many values are gonna be stored, or how many dimensions that are gonna be stored here, which we call the value of n and n, which how many index, or how many blocks, or how many pointers are gonna be produced here. In this case, we have 1, 2, 3, 4, 5, but we have n in the key 2, and we have m in the key 1. So m multiply n is going to give me exactly how many points I need to store here. So I have to give me the dimension first, how many values in the key 1, how many values in the key 2. Okay. Then after that, you have to give me the value that you use, or the grid coordinates, or the value that you use in order to decide the membership, or the use in order to compute the grid lines. Remember in our example we said 50, 70 for the age, and for the salary we said I think 50, 70, 99, and 200. So all these values can be stored here. Then after that, either going to do this one column based or they're going to be tuple based. You have to be aware, whatever the values, I mean, the way of direction you're going to use with the one going to keep, you need to keep the way that store the data in consideration, because you need to find a way, how can we locate the data within here. And here we have just a pointer and multiply in pointers in order to store all these pointers. This is how can you represent the index. So this is like the logical, this is how it looks like. I mean, how could we imagine that? But this is actually how the data can be stored in the desk, something like this. But this, the logical representation is gonna help us in order to visualize how the data can be stored in there. Okay? So here are the grid lines and the intersection between the whatever the value of key 1 and key 2, and gonna decide what, the region, or we call this one the bucket. The bucket is gonna have a pointer to the block where the data can be stored that located in this bucket. We have a different ways in order to build the grid lines or the value that coordinates or value coordinates that you use in order to decide or use as a grid lines or decide the membership within each bucket. The first one we're going to use individual points, and the second one can be used as an interval. I think we say it's better to say when we say individual points, that means we're going to use discrete value. So take a look here. Assume that we're going to use discrete value or individual. That means in this case, all the values are going to be stored here. The value of key 2 equal x1. And here, for example, all the values are going to be stored here. The value of key 1 is equal exactly v2. So here, we call this one discrete value. Okay? So when you say hash, you say x5, or just say x3 and v2. So in this case, you have to go x3 is here, this location, and or this direction. v2 is going to be this direction. So I'm trusting just to bring or retrieve this block, the intersection between them. So here just to have the actual value. Okay? This is the most common way in order to represent the data as interval, because this one allows you in order to store, or have more flexibility in answer many query. Okay? So in this case, it's going to be interval, which is similar to the P plus 3 and so. If you look, you have like, assume that you have a node that contains K2, so it looks like you have X1, here the pointer to the older value of the less than X1, and you have another pointer which is going to be the value is greater than or equal X1 and less than X2, and etc. Yeah, this is similar to this representation that we have as interval here. So here we're not going to have what? If they have n value, or n pointer, or n value, that means in this case we have n plus 1 interval. Yeah, because you have to say what? We have one, for example, you have 3 value, x1, x2, x3, then you have the values that are greater than x3. Okay? And also, that means you have, if you have n pointers, that means you end up with have n plus 1, let's say, interval here. Or n grid lines, that means we have n plus 1. That means we have x1 up to xn, that means we have 1, 2, 3, 4, 5, up to n plus 1. And here again, when you try to specify the value, for example, I give you like the value x2 and v2, in order to answer this question, hash for x2 is going to be, find the value where the x2 is going to be equal. So that means I'm just looking here, because, sorry, I hate that. x2, v2, x2 is going to be this direction, yeah? Because x2 is going to be greater than or equal x2 less than x3, so this is the area that we're looking for, and v2, this is the area that we're looking for. Yeah, because this one, and that's what I need to retrieve. This block. So see, that's the meaning when we say hashing, but we are not hashing. We are not going to compute the hash value, but we're going to use like the search key values in order to locate to decide which, for example, bucket that we need to retrieve. Okay. This has an example. Assume that we have the information about the jewelry who buy, people who buy, jewelry. So I'm not interested about the rest of the information. I'm just interested in the agent that's selling. Assume that we have more information, but we need to build the index based two-dimension agent salary. Okay. So for example, from A up to L, we have this 12 entry. Okay. So A, that means age 25, and the salary is 60. I'm using this one in 1,000, so it's 60,000. Okay. So in order to build this index, this is a simple thing. Someone asked me, how can you build the index? Maybe you can divide this one into 2 halves. Then after that, you feel like you have like too many or too much discomfort, or let's say overflow. That means you have to divide more. Okay, that's or maybe use the median if you try to use or divide or build the index. Anyway, assume that we're gonna do what? We're gonna build the index based on the 40 and 50. We have two grid values, and we're gonna use interval here. That means it's gonna be, if you have two values, the grid values, that means you're going to have in 2 plus 1, I mean region, or let's say pointers here. So here that means all the values are gonna be less than 40, or the age less than 40, and here the age is gonna be, let's say, greater than 40 and less than 55, and here greater than or equal 55. By the way, you can write this one down here. I mean, x and y-x, you can say age and salary. Okay, so either is fine. This is the common way how to build this one, x-axis and y-axis. So we can have 40 and 55, and here we can have 90K, and we have 225. Okay, and the stores information. So just to give you an example, let's take a look. How can we store this one, the third one, or this circle, or the point of this circle in the index 50 and 120. So 50, that means in this case the age is going to be this area, and 120, this is going to be where? It's going to be in this area, on this location. So the intersection, this is the bucket that you need to follow to the block where the information is going to be stored here. You take a look here, you see that closed information. When you say closed information, that means the age 50 and 120. If you take a look here, 50 here from 40 up to 55, anyway, 55, and the salary between 90K up to 225 must be stored to each other, close to each other. So we have like related information can be stored next to each other. Okay. By the way, we're going to use this example for the rest of the other data structure that we're going to use. Okay. So this is the way how to insert this one. This is when you're using, I mean, discrete value. Okay, and this is when we use this say interval. Interval, that means, you remember, we have n pointers or n value. That means we have n plus 1, let's say, value. Okay, a pointer, or n plus 1. We can generalize this one if you have a 2 dimension to the 3 dimensions. That means you have to give me the pointer 3 dimensions, the first, the second, the third, the number of grid pointers or values that we have. Then you have to list all the grid values for the first dimension, for the second, and for the third. Then after that, you have n multiply k pointers if you use discrete value as to represent, I mean, the grid value. If you use interval, that means if you have n, that means you end up, we have n plus 1. So that means you have n plus 1 multiply n plus 1 multiply k plus 1 range pointers here. This is, I mean, the index. If you take a look, this is how the textbook is going to represent the data here, the index. And here, it's better to visualize the idea here. If you figure out or find out you have money data that can be stored here, so that means this bucket is going to have too many overflow. So it's better to do what? I'm going to be divide or add, introduce another grid value here. Or maybe have another grid value here. So it depends. Okay? So you can dynamically modify that. Anyway, how can you look up? How can you search here? If you try to find something, you have to compute the hash value. When you can say the hash, I'm going to just locate, give me the XY axis of values in order to locate the correct bucket. Yeah? So give me the age, for example, 50 and salary 100. So the first thing you try to do, what? Let's go here. 50 and 100. So what I'm going to do here, I need a bucket here. So first you need to locate the correct or proper bucket that you need to perform. X and Y, age and salary, locate this one, then after that, this one, follow this pointer. We assume this one is going to be resides in the main memory because the size is too small. So it looks like an array or directory that we use in the hash index, hash table. Just to have a hash value tell you where the pointer to the actual bucket where it is going to be stored, something like this, okay? So this one is going to be bucket. The bucket is going to say, okay, go to the fetch the information of this block. You have to fetch this block to the main memory. Then you can perform searching in order to figure out the search key that you're looking for is exist or not. And here, since hash I cannot, or hash-like index, we cannot tell whether the indexes or the values exist or not until to perform the search. So assume this one, you didn't find this one in the first block. And this one, we do have an overflow. That means you have to perform another discount out operation in order to fetch, the overflow block. In the main memory, perform the search. So the performance depends on what? The number of overflow blocks that we have. Yeah, in this case. This is how can we look up for the specific. That's summarized here. So how can we insert? Just so we give you the performance, yeah? How to insert this one. First, you have to search, locate the proper, bucket, fetch the block, the first block that's associated pointed by this bucket. If there's a space, you fetch the memory. Do you have a space? Yes. Insert a new item, then reflect or rewrite the block back to the desk. If it's 4, what you need to do, you are going to create a new bucket, a new block, insert a new item, update whatever, the pointer from the main block or the first block to the second block, then you have to reflect the change in the desk. So that's what we summarize here. So the performance in general, assume it looks like in order to search the best case scenario, assume that the grid index can be stored in the main memory. So when you locate which bucket, it's gonna be cost you nothing. Okay, compared to the number of disk input out operation. The only thing you do in the best case scenario, you need to perform one disk input out operation in order to fetch the block that contains, let's say, the search key that you're looking for. If the bucket that contains multiple, let's say, overflow blocks, that means you're going to perform, it depends on the number of disk, overflow blocks you're going to perform here. Okay? So the insert is going to be what? First, you have to find the proper location of the bucket, costing you nothing. Then after that, you have to fetch or find out the bucket that contains space, enough space in order to set the element. If the first one contains space, fine. If not, that means assume this is the case. This bucket is going to point here. We have 1, 2. This one has a space. So here I have one disk input out operation. There is no space. The second disk input out operation, there is no space. I need to follow the overflow. The third one, we already have a space. Then in this case, I need to insert the item. Then I'm gonna, reflect only perform. In this case, we're gonna perform 4 input out operation. The 3 of them just to find out the block that contains place or have enough space, and the 4th one in order to reflect or rewrite, the blocks that I modified. If there is no space, the last one, and there is no more block, it's gonna be worse in this case. So what I'm gonna do here in this case, I'm gonna introduce a new block here. This we have different color. You create a new block bucket, store the new item here. Then you need to update the overflow from the previous one bucket to the new one. Then here in this case, you're gonna perform what? It's gonna be 1, 2, 3, just to locate the bucket or the block. Identify the base, create another one. That's not gonna cost me anything here. I update this bucket block and this bucket or this block. That means we end up we have 1, 2, 3, 4, 5 disk input out operation in order to store the item or the element in the place. So we don't like overflow, okay? Because overflow is gonna cost us and gonna affect the overall performance. So let's take a look. Since you said okay, the most important thing I need to take a look here. I introduce you to different query. Okay, and you're going to see whether this the way that we build an index is going to help us in order to answer this query more efficient way, or just we waste our time. Okay, we don't actually, but let's take a look. So the partial match query, I give you, for example, in this case, either the age or the salary. If you give me both of them, it's fine, but just because the partial, because that's the ones that is not easy to answer. So assume that I give you find all the jewelry purchased by people with age equal 50. Okay. So in this case, I give you one value. So it looks like you can compute by the age. And the age is going to tell you, for example, the value is going to be where the location of the bucket that you need to retrieve in this direction. Okay, so in this case, you have to follow this pointer, 1, 2, 3, in order to retrieve the best case scenario. Assume that and we don't have overflow. I'm going to perform 3 disk input out operation to the main memory. Then you can perform the search. So it works fine. Yeah. And the second one, or the kind of query, the range of query here. This is one interesting query here. You see that here? So it looks like I'm looking for what? Assume that this is just to imagine how this piece looks like. So we have 40, we have 55, okay? And here we have, let's say, 90, and we have 225, yeah? So what I'm looking here, I find all the jewelry, okay, purchased by people, and the age between 35 and 50. So it looks like I'm looking at, let's see, 35 and 50 here, okay? And you say, I see this one's not yet. And the salary is between the 50 and 100. So I'm looking for this one. So I'm trusting in this area, yeah? You see that using this index, all the information that you're looking for related to each other, it's going to be stored either in the same block, because that's what I'm trusting in, and this is the way how I'm stored my data on the disk, right? You see that? The information related to each other going to be stored next to each other. Either it's going to be in the same block, if I'm lucky, or at least I'm going to perform this compute out operation in order to access the data. So it's not going to be random. It's not going to be cost me or enforce me in order to perform the say random disk input out operation. So here, using the structure that we have, oh yes, we can also this one more efficient. Wait, so this case is going to have here 35 and 50 this direction, or this option, or this way, and this is for example here we start from here to here, yeah. So I know we're supposed to have a bottom up, not a bottom top down. Anyway, so this is going to be the area. It's going to be between what? Oh, the salary between 50 and 100. So it's going to be located in this area. That's what I'm trusting here. So here it looks like I need to have this 1, 2, 3, 4. I mean, follow the pointer that's associated with 4 buckets. So we're still being able to answer this one more efficient. Since I didn't perform sequential scan, since I'm not going to perform this random discovered order operation, at the same time, the related information close to each other can be stored, let's say, in the same block. Oh, they close to each other. Okay? Nearest neighbor queries here. Here, in this case, the data that contains points on the map. So assume that you have a point of interest, whatever restaurant, location is, whatever. Then I'm looking for each point first. Give you the scenario that we have is stored as a point X and Y. Okay, I give you X and Y in this case. Then I'm gonna ask you, for example, this is just a description. How can we answer the nearest neighbor query? Then I give you a specific point that have the value of X and Y, assume that 10 and 20, this point, and I say find the nearest neighbor for this, the closest point to this point. Of course, you're not gonna take measurement for every single point by yourself. I need to do this one automatically. So this is the query that we're going to use here. That's usually what we're doing in the nearest, neighbor queries. What we're going to perform here, we need to compute the distance between this point with every single point. This is the naive solution. So we're going to take the distance between this point and this one, and this one and this one, 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 all of them. Then try to find the one that has the smallest distance. This is the naive solution. We are not going to do this one, of course. I'm not going to perform sequential scan. So how can I do it? We need to use index. We're going to perform something here. I'm going to assume this is a query we're going to say. I'm going to say this point, I'm going to use correlated queries, subquery, correlated queries. Okay, so this means the value that from subquery is going to be what? Evaluate one time for every single value that we're going to get it from the outer query. Yeah? We studied this one in the database organization. Anyway, I'm going to say this point is going to be is the closest point if there is no exist another point closer than this point. And this is the query that you're going to perform here. Of course, we're going to Euclidean distance. Generally speaking, we have to compute the square root. But since we're going to, even without square root, the quadrant, compute the quadrant value, it's going to be allow me to answer the query. So it's fine, there's no need to compute the square root. Anyway, and this is my query. How can you perform this one using whatever, the index that we have? The data can be like this, and they need to find the nearest neighbor for this point, okay? Of course, they take a look, this is the nearest neighbor. And again, I'm not gonna perform sequential scan. A solution, compute the distance between every single point, find the smallest one. So what we're gonna do in this case, the first, you need to compute, I will find the nearest neighbor or the nearest neighbor point in the same bucket. So this one is going to be already in the main memory. So I can compute the distance between every single point within this bucket. Yeah, related to this point. And you choose the smallest one or the nearest one. I'm going to say this is the nearest neighbor candidate. The one that I found at this moment. Okay, this is going to be changed maybe because this is the smallest point or the candidate that I found in this bucket. Now I need to decide which bucket I need to compute, which the area. You need to decide the area that you need to, or you need to compute what is called the search distance, or the area you need to search. If I manage to find the distance or the circle from this point until this point, this means if there is any smallest point to draw a circle, this means if there is any smallest value or the closest value, the nearest neighbor, rather than this point that chooses as the candidate must be within this area. All right. So definitely not this point, not this point, not this point. Anyone maybe within this area or this circle is going to be candidate. Okay, so right now I'm going to say, okay, using by this distance, the search distance, I can't tell it, say, okay, I need to search here, I need to search here, I need to search this pocket, I need to search this pocket, I need to search this pocket. You can identify this pocket that you need or the area that you want to perform. Now jump to the first one next to me, either left or right, it depends on you. Now go to jump to the next block. Now you need to do what? You need to compute the nearest neighbor. Find in this area, find all the points that within this area, and compute the distance, and to check whether the distance that you compute here to here, whether it's going to be less than the distance that compared to the candidate point that you have or not. If you found any smallest distance of the points that located closer, then it's going to say, okay, this is the new candidate here. If you find a new candidate or smallest, let's say neighbor of that in the new block or bucket, what you need to do here, you need to compute the search or update the search distance. Now, if you found this one, the smallest one, so that means I need to compute a circle here and say, okay, if there is any small value here, it's going to be only located in this area. Okay, so now maybe one of them is going to locate, maybe you say, okay, you didn't need to compute another search. I'll assume this is search, maybe you're going to be giving me like this. I say, okay, exclude this area. You didn't need to compute because this one is not going to within the circle. So now I need to compute here and here and here. So you're going to continue doing this one of every single block you fetch. Try to find any node or point closer to the candidate. In this case, update the candidate neighbor. Then you compute the search distance because this one is going to reduce the number of blocks that you need to access. So that's what we did here. First here, compute the nearest one of the smallest value area, the search area. Then it draws a circle. Then I decide those are the candidates that you need to search there, or the blocks or bucket that you need to search. Fetch to the second one. Those are the area that you need at the beginning. Find the nearest neighbor. Another on the new bucket or block. I found one, another point closer to the candidate. So update the candidate, nearest neighbor. Then after that, you need to compute or update what you call the search distance. Definitely going to be smaller because you found someone closer. Continue to this one, and you see that if you found smaller one, it looks like you have from here. It looks like I'm going to exclude this one. It's not this. So reduce the number of discounts out operation you're going to perform. Continue doing this one until you find the value that you're looking for, or until to find the one closer, then return. That's what we're doing with the nearest neighbor. If you try to build my index in this case, okay. One more thing, just to 1 minute, then I will stop. Okay. Here, where am I? In order to answer this query, we cannot answer this query using the grid index. The only way, or the, let's say, structure, or index structure, allow me to answer this kind of query, we call this one the region tree, or the R tree, which is going to be discussed later. I tried to discuss what? I tried to use some data structure, that's the one that we're going to see, or we're going to use right now, if you're interested to work with a spatial database. If you take a look at different types of index, you're going to see some of them use the grid index, many of them use KD, and also the R tree. So they use them in order to represent the data as an object, in order to answer this kind of query. Okay, I have an issue related to the grid indexing. The major problem in the grid index, we call this one the poor occupancy rate at many grid buckets. Take a look at this bucket here. It's empty, right? So the situation gonna be worse if you have the 3 or more dimensions. So if you flip this one, you have, for example, more dimensions here. So this one maybe have like 1, 2, 3, 4 or more spaces. So the more dimensions that you have, the more that you have maybe many, let's say, empty buckets. Which is not a good solution here. If we have too many empty buckets, because here it's going to be reserved one block, of course the block is going to be empty, but I'm going to reserve this place in the memory. So it looks like the way that you organize the data not efficient. If we manage somehow to reorganize our data among all the buckets that we have evenly among these buckets, that's going to be a great solution. Okay? So let's take a look at the different categories, as I mentioned, the tree-like structure. I guess it's going to mainly just quick review about what you study in the data structure and the algorithms class, at least with different trees that we have. And yeah, this is going to be too easy for you. So in order to start looking at the k-dimension or KD, this means it's going to be k-dimension. It might be 1 dimension, 2 dimension, 3 dimension, etc. Tree, the structure. And the structure of the k-dimension is similar to the structure of what we call the binary tree. So first I'm going to introduce you or review with you the main memory version data structure for the KD tree. Then after that, I'm gonna say, how can we modify this one in order to store that using the KD tree after made minor modification in order to allow me to store the data on disk. Okay? So first, you are familiar with the binary search tree. The binary search tree, the binary that has the following, properties. So it looks like we have a node here in the middle. All the nodes, okay, in the left subtree, if this node X, if you give you node X here, all the nodes in the left subtree, all the value must be less than the value of X, right? Or the smaller value than X. And all of the value for all the nodes, or the value of the nodes in the right subtree of the node X, this tree has a value greater than the value of X. So here, we give you an example, and this one I'm gonna be hold of this property for every single node in the binary tree. So I'll give you a quick example here. 3 here. So this is the left subtree, all the value less than 3. And here, all the value of the right subtree must be greater than the value of the X. You can go, hold this property can be held for the, as long as it goes down here. Here, there is no left subtree. If there is, it must be less than 1. And here, the right subtree must be greater than 1. And the same thing here. All the left subtree less than 6, and all the right subtree is going to be greater than 6, and etc. That's the property of the binary search tree. Okay? So the KD is like generalization of the basic binary search tree. So it looks like you can say the KD tree, the main memory data structure, looks like you have, let's say the binary search tree is equivalent to 1. 1, let's say, value of k is equal 1. So in this case, it could be one-dimension tree. They have only one dimension that you use in order to, organize by data. For the k dimension, might be more than 1, 2, 3, 4, and etc. So we said it's generalization of the classical binary search tree. Okay, but we have one exception here. The search key that uses at different levels. So it looks like we have a different level. We start level 1, then you have a level 2, and etc. For each level, we're gonna use, or partition the data based on what is called one dimension. So assume that we have the 2-dimension KD tree, the dimension X and Y. So maybe the first level is gonna be based on the value of X. I'm going to classify, or to say, organize by data. Distribute the value based on the value of X. All of them is going to be in the left subtree less than the value of X, and the right subtree is going to be greater than the value of X. Of course, we have minor modification. Then in the next level here, I'm going to distribute the data based on the second dimension, which is the value of Y. The third level, since we have 2 dimensions, back to the value of X. So look again, well, the search key is going to be used at a different level, belongs to the different dimension. And the different dimension can be what is going to be circulated. So you have a 2-dimension, the first one X, the second one Y, the third one back X, the fourth one Y, and etc. If you have X, Y, Z, so the first X, the second Y, the third Z, then after that, the fourth X, and etc. Okay? If you are interested to take a look to the trees, I know they have, I give you like this link. If you want to learn or talk, read more about these kind of, say, multidimensional index in general. Here, just to give you an example using the Postgres, I'm planning to collect all the links that I want from you, or encourage you, or advise you take a look in order to gain more. So here for the Postgres, I will give you some links related to the Oracle. So we have 2 different data structure, database management system. I encourage you to take a look at them in order to, maybe you need them in order to help you, in order to make your life easier, or make the application that you work on much easier. So here for the first dimension, it's going to be x1, okay, base x, and the specific value of x, whatever value of x at the time. So all of them are going to be less than x1, and the right subtree is going to be greater than x1, yeah? And here, the second dimension based on the y. Of course, we have different values. So the left subtree is going to be all the value listed that is y1. Let's say all the value is going to be, y1 is going to be greater than all the value here. All the value is going to be less than y1. And here, all the value is going to be greater than the y1 here. And etc. Of course, so we say y1, all here, all the value must be less than the value of x1. And that's the structure here. Less than x1, the value of x must be less than x1, and here must be greater than x1, and you can go this one and get propagate the property for every single level here. Okay, The only thing we need to have the data. Where is the data going to be stored? Okay, the data going to be stored here in each node or every node. I'm talking about the classical version of the say in-memory data structure that you use in order to hold or to represent the KD tree. Okay, so here in each node here, I'm going to store the actual value. It's going to be here the value of x1 and y1. Here it's going to be x2 and y say x2 and y2, and here x3 and y1, and etc. This is the content of the data that you need to store the information here. So now let's take a look at the minor modification. I'm not gonna use the in-memory data structure in order to hold this tree structure. So what we can do here, we're gonna do minor modification. We call this one in order to make sure the KD3 can be used in order to store the data physically on disk. So the interior nodes or the inner node, they're not gonna store the data in the inner node. Only store the data on the leaf node. So it looks like the same structure as the B+3, but not exactly. Inside the internal node here, we're going to have what? I'm going to store 3 pieces of information. Since we have a multiple dimension, I need to specify based on what dimension I need to use in this level to partition the data. X or Y. Assume that we have 2 dimensions, okay? Then, the dividing value. What's the actual value of X? What's the actual value of X? Might be X1, X2. What's the actual value that you use in order to divide this dimension? And also, we have a 2 pointers to the left and the right, or 2 children. That's the inner node. In the leaf node, you're going to store what? The actual data. It's going to have the search key and the pointer where the data is going to be stored. So the leaf node is going to contains, the index entry that we need to store on the disk. Okay? So let's have an example here. Assume that this is the data that you wanted to store, dually as usual. So we do have an age salary. Okay, of course we have a more or to say columns, but we're not interested in these columns that be stored in the data. Okay, so we have the age and they have a salary then. Assume pointer where the actual rest of the data can be stored. Okay, assume that we're going to build my index or the key tree based on the first dimension is going to be the salary. Maybe we can use the median value, so we can divide the data into 2 parts. If it doesn't work, we need to adjust that. It's not our goal here, just to give you an idea how it works, how the structure looks like, then see how can we use them later. At least makes your life easier, hopefully later, if you decide to work with them. So the key data, the first one is going to be the salary. So all the data is going to be the left side of subtree is going to be less than 150 for the salary, and the right subtree is going to be greater than for the salary here. Okay? One thing I missed here, I need to modify something here. Since remember, we work with the KD tree, in general, we said the generalization of the binary tree. So here in the left side, less than the value of x1, and the right side greater than the value of x1, and you move the equality to the right side. So the right side is going to be all the value greater than or equal x1. So equality is going to be the right side. Okay? So here, all the value of salary less than 150 is going to be the left subtree, and here the right subtree must be greater than or equal 150. So you check all the value is greater than 150 here. And the propagate is going to be the same property going to be held while you're going down to traverse the tree, go down to the tree. Okay. Here for the second one, or the second level, based on the age 60, all the value in the left side of the left subtree must be less than 60, and all the value of the node value for the x or for the age actually here is going to be greater than or equal 60, and etc. Okay. And the leaf node is going to be what? Here it's going to be 1 block. For every single node or leaf node, it's going to represent the data on 1 block. The entire block can store the data there. Okay, and here we're going to have the index entry, the search key, and the pointer where the total data can be stored on the disk. Okay, I didn't need to go over this one because just summarize what we did right now. And this is 1, 2, and this is the actual value. Okay. So this, for example, yeah, I'm looking for value, by the way. Yeah, I thought that just described it. Anyway, what if I said you're looking for the salary less than 150 and the age less than 60 here? How can you perform the search here? You start with the top here. Yeah, if your salary less than 150, you can't tell either you're going to go left or the right. Yeah. So you can say the value less than 50, so then go this direction. Less than 150, that means this direction. And the age less than 60, that means you're going to go in this direction. So this tree, if you try to implement this one, this is the way how the text box is going to perform that. You start with the first dimension, first value used here. You have the, let's say, the dimension value with x and y, in this case salary or whatever age, was the value, and we have a 2 point. That's in a node. So generally speaking, you have the search space is going to be divided into 2 parts. Then for each part, with search space, you are going to divide this one into 2 parts based on the second dimension. And you're going to repeat this information. So each part of the subspace will partition each subspace into half based on the value of the second dimension. So here we have less than 150, we divide this one based on the age. Less than age, 60 and greater than equals 60, and etc. And continue doing this one. So this one is corresponding exactly to this one. The same structure. Okay, how can you use this one? So let's take a look. How can we apply the query that we talk about, and that'll help us to know that how can we answer the let's say multi-dimensional queries, if we call them multi-dimensional queries, the four different types of query. The first one, partial match query. How can we execute this one? Just I want to go over the search algorithm that we're going to use here. So if you start from the higher level, from the root of the tree, then after that, it depends whether this root of the current level that you reach right now, whether it contains information about the value that you're going to give it or not. Remember, the partial match query is going to give you what? I'm going to give you only, say, the query is going to specify the condition on some dimension, not all of them. So here the age and the salary either give you the age or the salary. If you give me both of them, that's great, perfect. So you're going to help me. But just speaking, the partial query, match query, you're going to give me one of them. So it depends on the dimension. If I'm reaching the specific level and I check the dimension value of this level at this level is given in the course of the query, then you can tell whether you go to the left or the right subtree. If it's not given, that means in this case you cannot tell. That means you have to go and investigate the both direction. Okay, you have to go to both branches. So for example here, I said find all the person with their age 35. Which my age? Multiply by 2. I guess. I used to be 35. Anyway, you start with the top here. This is my, the salary here. Can you decide based on the salary here of the value that's in the search whether I go to the left or the right? No, I can't. So in this case, I need to investigate or go to both branches. Just for simplicity, go to the left branch first, then after that you get back to that. So here you have to go here and here. Good. Let's go to the left first. Here the age. Oh, I know the exact value because it's given in the query. So I can't tell whether I go to the left or the right. Here in this case, I'm going to go to the left because all the value less than 60 is going to be in the left subtree. Now I reach this point, salary. I can't tell because the value of the salary wasn't given in the predicate of the query. So in this case, I need to go to investigate the both branches. Let's go with the left first. Age 35 and the age looking for equal 35 or age 38. So I can't go only decide in this case based on the query that we have. I need to go to the left subtree. So in this case, I'm reached this point. This will achieve 1. This comes to our operation. This is 2. And for this one, since I'm done from this left subtree, let's go with the right subtree. At the age 46 or 47, and I know age 35, I know that I go to the left. And here for the salary, you have to investigate or go both branches. So I have 1, 2, 3, 4. This comes out operation in order to answer this query. So like an efficient way in order to answer this one. That's good. Good. How about the range query? Again, I remind you of the range query. So I'm going to ask for the objects that lie either entirely or partially inside the specific region. Give you like specific area, tell me what kind of objects are within this area. Okay? So the same thing, since here we have, for simplicity, 2 dimensions. And we have multiple levels, each level is going to be based on a specific dimension. So here you check the search range and see whether the search range, whether it's going to be completely contained with the left subtree or the right subtree. If you can tell, based on the search range, for example, in the salary, based on the value that we have in this level, I can't tell whether it's going to complete the left or the right. I can't go with either the left or the right in this case. If I cannot tell, it's not completely contained in the left or the right, this means the value is going to be in between. So in this case, you have to go, you have to search in the both subtree in this case. Just take a look here. I give you the range between age 35 and 50 and the salary between 50 and 100. So that one, we'll start at the top here. I have the salary here. And so I can just compare based on the part of the salary. The salary is 50 and 100, so it looks like clearly is contained completely in the left subtree. Yeah, because the highest value is less than 150, definitely this part is going to be left subtree. So I go here. Okay. Here for the age between 35 and 50, this is a predicate in the query. But I've said the age here, I know that, so it's completely, contained in the left subtree. Less than 60, and the age, the highest value 50, so definitely I need to go to the left subtree. Here for the salary here. I've said the salary, the value they divide here to left and right is 80. But here, anything less than 80 is going to be this side, and anything greater than or equal 80 is going to be in this side, of the right subtree. The salary between 50 and 100, so it's not completely contained, either the left or the right, in the between, both of them. So you need to investigate both of them. So I need to go to the left and the right here. For the age here, age the same thing here. The age is the 50, the highest value, and here the value is 38 used to divide whether you're going to go to the left or the right. So it looks like I need to go to the left or the right. So I need to achieve this. 1, 2, 3. Yeah, and with the 3 discount out operation, you see that you can perform this operation, get a 3 discount out operation, allow me in order to answer this query. So you build your index based on P+3, maybe you're going to cause you to perform too many discount out operation. So this is an efficient way in order to perform that. How about the nearest neighbor query? Can you do that or not? Just a quick reminder with the nearest neighbor query. I give you a point, or whatever object. Then I want from you, or ask you to find, the nearest object or the point that satisfies specific condition. It depends whether the closest point to this, no, the nearest point to this guy, or this point, or this object. The problem here, we cannot use this structure easily. And you can take a look here. You see that the nearest number of close point, for example, to the 50 and 149, this point, this is the closest point here. It's going to be 50 and 150. This is the closest point, the nearest neighbor for this one. But the problem with it is going to be, maybe it's going to be far apart from each other. Using this structure, maybe you're going to go up and down, traverse the tree, perform too many discount operations until find what I'm looking for. What's going to be expensive operation here in this case. So we said it's not easy way over to say it's not efficient. It uses this structure in order to answer the query of the nearest neighbor queries. Clear? Where am I? Query again, give a location, coordinate, then define the object that contains this location. We cannot answer this one. The only data structure allow me to answer this query. That means I need to use the R tree. That's why we need to cover this one more details. That's all that we wanted to know about the KD3, the structure, how it looks like, and you can build your data, index based on the KD3. Okay, so the quad tree, I'm not gonna cover this one, but it's similar to the KD3s. The nice thing with a quad tree, every time, this is a search space. Every time you wanted to say, create or divide this one, you have to divide this one evenly here. Every time you divide this one evenly. Every time you divide this one in even arranged and etc. So you keep this one, divide this one evenly until you stop dividing the data. That's if you want to have more space to store your data or your information. The RT is interesting. And the nice thing, because the RT is going to have a different way, how can we represent the data? Okay? Before we talk about this one, we need to define some terminology that are going to help us in order to understand what's going on here. So generally speaking, the spatial data is going to be organized into what is called nesting rectangle. Okay? So the smaller one is going to be nested in the larger one. So generally speaking, if you take a look at the structure of the, let's say, R tree, the search space. So this is the space, the whole. Maybe you have, let's say, one big one. I'm gonna say this one rectangle, and this rectangle maybe have, let's say, I try to use a different color. Okay, one, let's say here, and another one here. Okay, and maybe have a third one here. So here we have a different object that be stored here. So the structure we have like organized in the nested rectangle. The big one is gonna be in the top, the root, and when you go deeper, the big one is gonna contain, want to say, a subset of, let's say, rectangle. Okay. So it's similar to the B+3, but the B+3 we have a search key and pointer. Here we're going to use this rectangle and pointer. Okay? like regions of the data. So we need to introduce you to different types of the way, terminology used in order to identify the object within this R tree or the region tree. I'm going to define what's called the bounding box with the rectangle that's used in order to contain a group of objects. So if you have an object here, 1, 2, 3 objects, this is what is called the bounding box, which is the area here. So for example, either the black one or the red one or the orange one, this bounding box, okay, with the rectangle that contains, let's say, a number of objects. Clear? So this odd object, you can give me these 2 points here, and here it's going to be defined the area or the rectangle area that's used in order to hold all these or organize all these group of objects within it. We do have what's called the minimum bounding box. For the R2, by the way, we're going to only use the rectangle to represent the data. So the minimum bounding box here, with the smallest rectangle that I need to use in order to contain a group of objects. And most of the time we use the minimum bounding box in order to represent one object, not a number of objects. So here I'm going to have the smallest rectangle I can have in order to represent or contain all these objects. Or maybe sometimes you're going to use this amount, this minimum bounding box, one smallest rectangle that contains one object. Okay, so it looks like we need to use a rectangle. The question here, how can we represent this rectangle? So it looks like we have a points. Now we need a set of points in order to help me to represent this rectangle, right? So we can have, 2 points. We didn't need to have a point, 4 points. All you need, I need what? I need coordinates of the lower left corner and the coordinates of the upper right corner. Those 2 points is enough in order to represent any rectangle. So in this case, if we have any rectangle in the system here, assume that we have the big bounding box, and get a rectangle and a big bounding box. Okay, and can I say bounding box 1? So here I need, for example, x1 and y1, and I need x2 and y2. Only these points. So in this case, you can say x1 and y1, comma, x2 and y2. This is the bounding box 1. Then you can have a pointer where this is going to be pointing to the next level or the lower level or something like this. So I'm going to use these coordinates as a search key. So compared to the p plus 3 is going to give me a keyword value or search key value. Here, I don't have a search key value. In order to search, you're going to give me like either a minimum bounding box or the bounding box that you're looking for. How can you represent them? That means you have 2 points. Give me what's called the lower left corner and the upper right corner coordinates of this rectangle. So this is what I need in order to represent the data. Okay? This R tree, how it looks like, this internal structure, as we mentioned, going to be organize the data into nested rectangle, with the smaller one and going to be nested in the larger one. So here the structure, let's show you here. Here it's going to be have B here, BB1, okay? And inside BB1 we do have, let's say, BB2, let's say 2 and 3, just for 4, just for simplicity. And the BB2 here, with another bounding box, is going to have whatever the value here. This is how can, and all of them, maybe you have BB, this original one, that has a pointer to the lower level, something like this. Okay, you have a large box, inside large box you have a number of small boxes, a small rectangle. This is the way how to organize the data or build my data. So inside this one, I'm going to use the bounding box in order to help me, in order to, as a search key, in order to organize and find where my data I'm looking for. So this is a root, on the main root, on let's say the first level, and you have for every single bounding box, I'm going to have a pointer here. So what's this pointer means here? This pointer is going to tell me that it's going to point on all the objects that is going to be inside this bounding box. Completely inside of this bounding box. So what kind of object here? BB1, we do have BB2 and BB3 with a bounding box 2 and bounding box 3. So the bounding box 2 here is going to have, maybe they're either going to have another bounding box inside this one, or maybe you have a set of objects. This is what's called the inner nodes. All the bounding box point to the list of objects. Let's say all the bounding boxes that can be contained within or lie within this bounding box. Okay, let's go deeper and see what the content here, what's going to happen inside that. What do we have here? So inside this one here, I'm going to add, remember we said, okay, how can you represent the bounding box here? I need to have 2 points, the lower left corner and the upper right corner. So that's these points, this is what they're going to represent here. So we have a 10, 20, 50, 50 40, which is the bounding box, for example, 4, I guess, in our example, so simplicity. And here the pointer. What's the pointer going to be pointed to the child, to the lower level? We didn't have too many pointers. For every single bounding box, we're going to have a pointer to the lower level where, I mean, in the list or set of all the objects that completely lie within or contained or located within that bounding box. Okay? Okay. So here for the inner node, in the inner node, it's going to be different here. This actually is going to be the same, but remember, in the lower level, in the P plus C, we have a search key, then a pointer to what? To the actual tuple where the data can be stored. So here you're going to do what? I'm going to use the minimum bounding box with the smallest rectangle used in order to represent or order to hold or contain an object. And have a pointer, I'm going to have a record pointer here. It's not going to be pointed to the bounding box. I'm going to point it to the actual record where the data associated whatever this object will be stored on the disk. For example, it might be the object, can be the house, might be, say, the road, it might be building, point of entrance, whatever. Then you're going to have extract the associated information about this house. For example, house 1, the address, the information about this house, whatever kind of information can be stored on the disk. Okay? So we have a search. When you perform the search, I mean the R tree here, you're starting, for example, you're looking for an object or whatever you're looking for. You have like a rectangle, let's say in the minimum bounding box, or you have a bounding box. It depends what you're looking for. In most of the case, you're looking for an object. The object can be represented by minimum bounding box. You give me this value, and you're gonna say, I'm looking for what? Whether that's the way how to perform the search. Whether this minimum bounding box contains within this bounding box or not. I'm going to show you how to compute the contain. If contain, that means, okay, follow this one. Maybe the value is going to be stored here. If you didn't find this one in this direction, that means jump to the next bounding box in the same level. Okay? Because remember, if the object within the area, the coordinate of the object is going to be located within one bounding box, that means this object can be stored there. Because we do have, I'm going to show you later, we do have what's called overlapping. So maybe bounding box can be overlapped with the others, but the object can be stored only on one bounding box, not more. Only in one area, or only in one region, no more than one. Okay? So let's take a look here. Sometimes we have one bounding box here, the big one, and maybe this one you have one bounding box here, we have another bounding box here, and you have third one. It might be here, this situation. But you see, an object, here we do have overlapping here, and here we have an overlapping. But if we have one object here, let's have a different color here. If we have one object stored here, this object either going to be stored in this bounding box or in that bounding box. Not to both of them. I'm going to go over, that's why we need to go over the insertion. Although someone has said, why you need to learn this one? Just to give you an idea what's going on. When you insert the data in the R tree, that is going to be only stored only on one bounding box, no more. So take a look here, starting here. So we agree that we have overlapping. Good. So that's why you have, when you try to search something in this area, you have to investigate every single bounding box this object that contains or will be located on or lie on it. Okay? So assume that we have this information. We have, let's say, plan, a tree, or what, or let's say, a map, and you want to represent this map or data, whatever data that we have, going to be represented onto what's it called? I mean, on the disk using the R tree. I'm planning to work with the tutorial, but I'm not sure we have time to finish this one within this semester. So expect, maybe, even after the end of the semester, maybe I'm going to send you an email and say, this is the tutorial that I talk about, how can you use this, let's say, GIST or generalized search tree, or let's say the block range index that use the Postgres, how can you simulate, the short tutorial, how to use them, how to build your index, how to represent your data within this index, and how to access them, how to work with them. So it's going to be interesting. Hopefully, if you got time, I'm going to prepare it, but definitely by the end of the semester. This is the part that I need to, focus on here. So instead to talk about the theoretical part, maybe going to be, in the future, going to be like just tutorial how to use them. So it's going to make sense to you guys. Why you need to learn this one? How can you use them? So assume that we have a different object here. And here it depends on you. Maybe someone said, okay, maybe I'm going to have this big bounding box. Oh, sorry, this is one big bounding box. Maybe you have another one here, represent this data. Maybe you have a third one here. Maybe you have a fourth one. It's okay. Maybe you have a multiple bounding box. It's okay. You have multiple of them. At the beginning, we have only one bounding box. It looks like when you build the B+ tree. You can put everything in one node, right? Then after that, inserting the data, now you have to split. So you expand the data. The same thing that's gonna happen here. We start only with one bounding box, big one. Then we keeping, as long as we're starting modifying the data, that's gonna be increased the number of bounding boxes required from us to split this one. Of course, that means the big one is gonna be split into the smaller one, and etc. Anyway, so assume that we have this data, and this data is going to be represented as following. Assume that we're going to have the first bounding box between 0, 0 up to 60, 50. So this is the first bounding box. I give you only 2 points. Okay? And since we have a rectangle, in order to represent the data, I cannot do this one like this. It's not going to work. Or I cannot do something like this, of course. Yeah? So in this case, a rectangle, this will give you 2 points that require me to do something like this. So we do have an overlapping. But you see that the house and the road 1 and 2 is going to belongs only to the bounding box 1. And the pipeline here is going to belongs to the bounding box 2. Okay? So this is the first one, and this is the second one. You see the house one? Since we store this one in the first bounding box, this one is not going to be stored in the second one. Only one place. So in this case, yeah, so the points, you have 20 and 20, and you have 180. Okay? So the first bounding box, 0, 0, 60, 50, and the second one, 20, 20, 180. And this one is going to be point to the next level. Since the next level, we don't have another bounding box, so it's going to be the leave node. The leave node is going to be what? You have like a list of entry. It's going to have the index entry. Each of them is going to represent one. The search key, which is going to be the minimum bounding box, and the pointer to the actual record in the disk. Okay? Assume that each block can allow you to store only 4 entries. Or let's say an index entry. So that's why we have 4 here. Good. Of course, we can substitute the minimum bounding box with the actual data, but we don't have time. I mean, it's clear that what we're looking for. Okay? As I mentioned, there is an overlapping, but the object within this overlap is going to be what? Must lie only located on one object. This perform how can I do the search? Just to give you an idea, it's interesting just to take a look at this one. So the first search algorithm in R tree, you start with a search with a specific point. They give you 1 point and tell me where the point is located. Where am I? Which remember, this is the main reason why you need to study the R tree. Because I want to answer the where am I query. Give you 1 point and tell me what the list of all the objects that this point located at, or contain this point. So the first one, I'm searching, you have to give me a point, X and Y, and I'll give you all the objects in the R tree that contains this point. And the algorithm you're going to use is like a recursive algorithm. This is actually give you the pseudocode, just to give you an idea how it looks like. This is the algorithm. You're going to look up X and Y, a point. I'm looking for a specific point. Then later I'm going to take a look. How can we search for, let's say, an object? Here we start with N, which is going to be the root, the top of the tree. And here it's going to have the result. Since it's recursive, we're going to recursively call this one. Then at the end, we're going to print or display whatever we have in the result object with value or variable. Okay? And it's going to be the current node, and assume that the current node is going to be internal. So we start in the top here. Okay? Then, for each entry that you find in this node, what we do have here, we do have like in the node, in the first one, we have bounding box 1, for example, and pointer. Bounding box 2, and we have a pointer. Something like this, yeah? Add entry. For each of them, you have to search and to figure out whether or any of them look at the subject that contains this point or not. Can it tell whether the point contains the bounding box or not? Yes. Because if the point is within this range or the rectangle, then it's going to be containing this bounding box. So what we're going to do here, for each of them, remember we do have overlapping, that means you have to perform search for every single bounding box that satisfies this condition. I need to do what? Recursively go to the child of this bounding box. In order to call this one, I'm going to call the lookup, the same value X and Y. The only difference in the end is going to be the pointer here with the child. And here I'm keeping have the result. I'm keeping do this one. For every child tree, or the, let's say, level or node, I'm going to perform this operation for every single bounded point is this one. If they find any of them, or for all of them that you found they have the match of the points that are located in it, you have to follow the pointer to the child and continue this call recursively until you reach what eventually, hopefully, you're going to reach a leave node. If you reach a leave node, so what we're going to do here, I need to find what, whether the value of x belongs within, let's say, the minimum bounded box, because in the leave node we have like the minimum bounded box, and have a pointer direct minimum bounded box true, and you have a pointer, and etc. So I need to check if this one to find which object does it contains this point. If you find of them the minimum bounded box for a specific object that contains this point in this case, that's what I'm looking for. It's going to be added to the result. I need to list of all the objects and continue doing this one. If here in this leave, or this non-leave node, you don't find any of them that contains this point, then in this case, you return blank or empty. This is the search. Okay, let's go over this one, with a quick example. So see, I'm going to give you this point, or this diagram, or this map, and I ask you just to find out whether, find all the objects that contains this point. Okay, so we start here, and what? You start in the top, and for every single bounded box that contains this point, you have to follow the child. Call the child, substitute the pointer with the child of this point, this node, or this, let's say, entity, or the object, then continue until you reach the leave node. So it's clearly it's not in the second one. Here is not here. The point is going to be included here. And this was 40 and 70, because the 40 and 70 is going to be located here. So it's not here. Here I need to follow the child. A child, if you have more, keep doing this one recursively. If you have a more than bounded box that contains this one, you have to follow all of them later. So anyway, I follow the pointer to the child. We are lucky we reach the leave node. Within the leave node, you have just to check which the minimum bounded box that contains this point. And here to check, just go back to the example here. Definitely going to be in the school because I don't have the coordinates here. So here it's going to return, I'll add the school. You see, it's going to be part of the result. And continue, maybe you have many objects that contain that. And just here to simplify the process that we did, just summarize what we did here. Okay, if it's not in the left, to check with the right, it exists, and we are fine here. Okay? How about if you find this point here? Where am I? You're stuck in the top, you're on the intersection, for example, the road 2, and maybe we have a pipeline or another intersection, another road. Or maybe you're out here in this area. So anyway, in this case, we're going to perform the same work. So we start at the top, you need to search for over every single bounded box that contains this point. We see that the first one, yes, and the second one, yes. Let's go with the first one first. You follow this pointer, you're going to find this one going to be located in the road, because I don't have the coordinates, but you know that exactly the minimum bounded box road 2 is going to contain this point. Then, continue for the next subtree, or say the other node, the other bounded box, follow the pointer. Here, you're going to find this one going to be in the pipeline. Yeah. So you're going to achieve all this information that you're looking for. That's how it looks like. How can you perform the search within, let's say, minimum bounded box? Or how can you search for the point? Whether the point is going to be located in one bounded box or maybe more than bounded box. Okay? One thing you need to take a look here, how can you search for a specific object? When you talk a specific object, that means you need to find a way how to represent the object. And we're going to represent the object in the RT using rectangle. We need to have 2 points that coordinates the lower left corner and the upper right corner for any object. When you say object, school, road, and whatever, okay? If you're looking for whether the object exists or not, you need to find this object located, or give you a range, for example, or find all the objects that within this range. Or give me where this object, I give you like coordinates to tell me what's going on, what kind of object that's stored in this area or within this range. So you need to find a way, in order to answer this query or the question, you need to define a new, let's say, comparison relationship. We call this one containment. I'm not going to say the question or query that we have less than or greater than or equal. No, whether this object is contained within another object or not. If you take a look to the GIST, okay, you're going to see that we have a different type of structure. You have, if you're interested right now, just you have the class, but we can't go over, for the Postgres here, let's give you GIST. Just Google this, click over this link, and you can see what kind of operation you can perform here. Okay, I sent you just a link with this one in the chat if you just take a look right now, quick, what's going on. So we do have a different type of operation, comparison operator we need to use. It's not less than or equal, contain, not contain, overlapping, in, etc. So we define this one, contain, the simple example. How can we define whether an object, or tell whether object is like contained within another object or not? So you see that if A contains B, that means the lower, say, left corner of A must be greater than or equal the lower left corner of B. And the upper right corner of A must be less than or equal the upper right corner of A. For B. Otherwise, A's cannot be within or contain this object. So this is the condition that we talk about. Okay? So in this case, if you have search for objects in the R tree, so in this case, similar to the previous one, but we need to have a contain. I'm not going to say belongs or equal within. Contain, okay? And here we're going to contain with a minimum bounding box with a bounding box. Okay, so it's going to be the same thing, recursive. We start giving an object, and they give you like, starts with the top, internal node or leave node, say root. Then after that, we have result, whether it's going to exist or not. What kind of object you're going to find here within this, say, coordinate or this rectangle that is sent it to you or give it to you. Okay, or whatever the object that contains the rectangular object here. Good. We start at the top, internal node, for every single, say, bounding box that contains this object, that you have to follow this one. When you say the object is going to be a rectangle, so it looks like whether this rectangle that contained within this bounding box or not. For every single bounding box this object contains, you have to follow them because we have overlapping. Maybe the first one is contained, but I'm not going to find the object there. The object may be in the other bounding box. So you need to search for every single bounding box here that contains this object. If you found any of them, or all of them that you find, this object that satisfies the condition can be contained, you have to follow to the child. This means go recursively call the child of this object. And continue doing this one until you reach the leave node. Somehow, one time we're going to reach the leave node here. So the leave node, that means I need to compare the minimum bounding box for this object with the minimum bounding box of the objects that's stored in this leave node, with all of them. If you find any of them that equal, that means in this case it must have the exact match. Then they're going to say, okay, the thing that within this object is a school or let's say whatever, road 1 or 2 pipelines, then done, stop. Because I'm looking for object. You find this one, it's going to be stored only in one bounding box. Then there is no need to continue the search. That's why you return and stop. Okay, how can you perform the insert? I know it's complicated a little bit, but at least it gives you an idea what's going on. We try to summarize everything in a few minutes. So here, if you try to insert an object or whatever, something into the R tree structure, within the structure. So the insertion structure is going to have what? Give me the minimum bounding box of the object because you're going to insert search key at the pointer, right? How can you represent the search key here? We're going to represent using the search key using the minimum bounding box here. Okay, and we do have, of course, the object's ID or whatever, the pointer or the data that store this object. Okay, and you start from the root every time. Then every time you're going to change. You start at the top until you reach find the first bounding box that have space that allow you in order to store this object. That's the goal that we try to perform here. I know the lengthy one, but it's easy to follow here. First, you start at the top. For every single minimum bounding box that you found here, for the null leave node, box 1, find the first one that can contain this minimum bounding box for the new object that you want to insert. Only the first one. I found this one. The object cannot contain this one because you know the minimum bounding box 1 here, the bounding box 1 here, the 2 here, and for example 3 here. Assume that the object can be stored here in the bounding box 1, 2, 3. So it's clearly this object contains only in the P1. So you follow this point. Even if the object can be stored here. So since you start with the first bounding box, the first one that can contain this object, follow this one. Go to the point, to the child. That means store this one in the first place or the first bounding box can allow you or can fit or can contain this object. So by this way, remember, we have one object. Even if we have overlapping, this object can be definitely stored only under one bounding box. Of course, in the top. Okay? At the same level. Assume that I found a place. One of them can be fit in one bounding box. So let me continue this one and try it until reach the leave node. Let's jump this one. I found one of them is going to be can be allowed, can be stored, or can be contained here. You reach the leave node. Sorry, I don't know why it cannot work this one. Leave node here. So check whether the leave node has space or not. Yes, has space. Insert it, then done. If the leave node doesn't have space, remember what we did in the B+ tree? You didn't have space in the leave node here. So what we're going to do here, if you insert this one, it's going to be overflow. This means you need to do what? Remember this scenario that looks like something like this. Let me clear this one. You have this one, for example, bounded box 5. And this one here, the leave node. Leave node, you have only, for example, 1, 2, 3, 4 space. I want to insert something here, 5. If you insert 5, it's going to be overflow. So in overflow, you need to split this one into 2 parts. So this one is going to be, let's say, 1 node and another 2 leave nodes, right? If you have a 2 leave nodes, this means, remember, the branch here must be split into 2, because this one, every single bounded box or every single entry must have only 1 pointer here. So I need to do what? I need to update the parent. So this means create 1 parent for this one, 1 parent for this one, and here we need to update the parent or split the parent from B51 and BB52, whatever, and each of them is going to point to the corresponding, let's say, leave node. What if I didn't find any bounded box can contain this element for the higher level? I'm not talking about the leave node. In the terminal, assume we have BB1, BB2. This is here, and that's what you have. This is BB1, and this, for example, BB2. And the element that I want to sort the object, it's here. It's not within any of them. So in this case, what we need to do, the system is going to try to do what? Try to choose one bounding box that can be enlarged, increase the space, or to say the area of one bounding box. Okay? In the way that one is going to add the least amount to the area of the bounding box. So maybe this one closes the bounding box 2 and going to be enlarge the size of the bounding box 2 here until it's going to be what? It can fit this object inside this one. Update the let's say the value. Then after that, now you can insert the object inside. There's many ways in order to take care of this one. How can you perform this one? How can we achieve this goal? How can you choose which bounded box is going to be increase the size? How can you split, the leave node or non-leave node in the way that how can you organize or distribute, to say, the entry within among, to say, 2 nodes? It's not our focus in this class, but at least it gives you an idea what's going on here. So I'll give you this example. I want to insert X here, and we have 1, 2, 3. So remember, each leave node can allow me to store 4 elements or 4, let's say, object. So this case can be perfect. So again, this one only in the one bounded box. The first bounded box contains this element. Follow the object. Follow this one. You have a space. I'm going to insert it here. I'm done. Okay. Assume that you want to insert the value of X here. It's not neither here or here. So in this case, someone is going to say, okay, since I'm not going to find any bounded box can contain this element, so I'm going to do what? Either I'm going to increase the value, or let's say the area, the size of the bounded box 1 or 2. If you increase 2, it's going to have too much area going to be added here. Okay, but for 1, it's easy because I'm going to increase, maybe this is the only area that's going to be increased here. So that's why, that's the way, there's many algorithms going to test to find out which bounded box you need to increase, the one that adds the least amount to the area. Okay, I'm not going to add more area, a lot of, space to this bounded box to recover. So augment this one, increase the size bounded box 1. Now when you increase this one by 1, or a little bit here, so this one is going to contain this element. So now you can insert this element. So that's what we did here. We didn't find anyone to insert this object X, a new object. So in this case, I augment this one, or increase the size of this one, this bounded box 1. Now I update the space, I will say the area of the coordinates here, actually the upper right corner. Now this one contains the new object, then I can store this one within this object. Here the other scenarios you mentioned, for example, what if you try to insert the element and the element is going to be like overflow? There's no space here to insert this element. And for example, assume that you want to insert the X here in the second bounded box too. So in this case, we already have 4 elements or objects stored there. So when you try to perform this operation, we cannot do that. I mean, we can do, but the problem here, we're going to have an overflow. So we see that we have 1 point, and bounded box 2 is going to point to the leaf node. I'm going to insert x here. It's full. So that means I'm going to split this one into 2. When you split this one into 2, since we used to have 1 bounded box here, bounded box here can point only in 1 child. Since we have 2 children here, that means you need to update the parent. So the way that which area you're gonna use for the bounded box here that hold this element, and which bounded box or area of the coordinates, or to say the rectangle, the minimum or the whatever rectangle, the bounded box that you use in order to contain all the elements of this new nodes, that's a different story, because you have many algorithms, many ways in order to figure out the best way in order to how can you represent or split the element among, let's say, non-leaf node and leaf nodes. Just to give you a hint here what's going on, or idea, assume that this is the existing bounded box here. After you insert an element here, you insert a new one here. So I add 1 here. So now we need to come up with a new bounded box. Someone is going to say, okay, maybe I'm going to increase this one a little bit. This is the best bounded box. No, this is not the best solution. Because remember, we need to figure out or find the minimum bounded box that can fit or can, let's say, represent the entire data. And the small bounded box you can come up with, the more accurate you can, let's say, represent the data. Give you an example. Assume this is your bounded box, a huge one, and this is the data here. Compare this one with another bounded box. Assume that this is my bounded box here. So here, since the bounded box is smaller, the red one, so I can, based on the coordinate value, the lower and the upper, the left and the right, I can tell whether an object can store there or not. But this one, the original one, the old one, is huge, big. It's going to cover a lot of, object, a lot of area, or a huge amount of data. So we cannot tell for accurately 100% whether the data exists or not. In both cases, we cannot tell 100%. But the small size of the rectangle of the bounded box allow me in order to represent the data more accurately here. So anyway, so we have different algorithms to both go over this one, so I'm not going to go over them. And that's all that I want from you to know about this kind of spatial data and the spatial multi-value index. You can take a look at the spatial data types in general, or spatial graph, or what we say guides to give you more information about this part. And remember, this course just in order to introduce you in the way that how to represent, let's say, hopefully, implement the database management system from scratch, at least give you an idea what's going on, how to create a buffer manager, how to store the data on the disk, how to retrieve the data on the disk. Then the main goal later, we're going to take a look, starting next lecture, we're going to see how can we process, when you send your query, how the database management system is going to execute the query. Go with the plans, different plans, how to anticipate the cost. And remember, when you talk about the analysis, when you select analysis, when you give me more parameters of the analysis, you're going to give me, for example, different plans, how the system decides which plan you're going to use, and etc. Okay? So now I need to talk about different types of index. It's the bitmaps index. Which one interesting index here? The bitmap, I guess most of you are not familiar with this one. Okay? So the goal here, the bitmap here, it looks like I need to find the what here. It's like another type of index which will store the data in the form of the bitmap array or vector. There's a different way to store the data here. And this type of index works perfectly, mainly for the data warehouse or the environment in which the query maybe has a reference to the columns, or they say add attributes that you use in order to build the index. And these attributes has like low cardinality. You know what you mean, the low cardinality? That means the number of distinct values is small compared to the number of tuples. Okay? Assume that you have the data, and your database, I guess the best example we have information about the student ID, name, etc. You can have a gender with a male or female. Okay? So here, what's the cardinality? M and F, 0, 1, or M or F, true. If you have 1 million record, the cardinality is true. So the nice way to do that, if I manage to build an index based on this attribute, which has a low cardinality, this is going to help me in order to answer query more efficient way. Which, if you are familiar with Oracle do this one. Most data or the other database management system, you're going to do what? Scan, bitmap scan. That's a different story. We're going to cover this one later when we talk about the query processing and optimization. But right now, you are going to build an index. Okay, Oracle do that. Okay, so based on what? Choose an attribute that has a low cardinality and then build an index. How the index looks like compared to the B plus tree. Here in the B plus, because I've said I'm gonna do what? Store the data in the form of what? Bitmaps array. When I say bitmaps, this means zeros or ones in vectors or array. Okay, so here for every single entry or value, I can say, assume that we have 1 million records, 100 records, just for simplicity. Okay, I'm gonna build based on the gender. Okay, what the unique value? Sorry, sometimes it's exciting to throw the pencil. Anyway, with the unique value we had only the, let's say, male or female. Do you have another unique value? No. Here I'm gonna have a let's say vector or the array. And the vector is gonna be series of zeros or one. And the number of bits is gonna be depends how many tuples do you have. So it looks like you have a tuple 1, 2, up to 100. Okay? And here we have 100 value, or vector that contains 100 bits. Here, for every single tuple here, you find in your data, if the corresponding value for this tuple for the gender is male, I'm gonna set this one to the 1. If the corresponding value for the gender here, for that tuple, or that record is not male, I'm gonna put this one as a 0. So only set the value for the gender equal male to the tuple that has this value. So here maybe you have 1, 1, and the rest all of 0, for example, and the last one is gonna be 1. And the rest is going to be 0. So it looks like tuple 1 and tuple 2 or tuple 100, the value of the gender is going to be male. And the rest is going to be female. And here that means 0, 0, 1, 1, up to 1, 1, and the last one 0. That means tuple 1, tuple 2, and tuple 100, the corresponding value of gender is fail, as you say, is not female. I'm going to be put this one to 0. And the rest, the corresponding value is going to be female. That means I'm going to set this one to the 1. You see that? That's what is called exactly the bitmap index. Compare this one with the B plus tree or the B tree index. The B tree index, the index value or entry is going to be stored as what? As a balanced tree. You see that we have a balanced tree format, and we're going to store the index attribute along with the tuple ID here. So here on the leaf node, in the top, you have, for example, search key 3, the pointer with the tuple ID. Yeah, for the pointer of the record ID. That's what you're doing in the B plus tree. Of course, we have like balance tree and non-leaf node until you reach the value of the leaf node here. Bitmap index, now. Each index entry, the key or index that we have here, okay, it's going to store the pointer to the multiple tuples. So it looks like here, when you see 1 and 2, it looks like I have a pointer to 1, the first tuple, the second tuple, and the 100. Because you can define which tuple I need to retrieve, which tuple I need to access based on the corresponding value that's stored in this tuple in this data. Okay? And it works perfect. For example, if you have, can I build bitmap index with the ID? No, it's a bad idea. Because remember, we said the bitmap index, it works perfectly fine if based on the attributes or the column that you have the data that have the low cardinality. With the number of value or unique value for this attribute or this column compared to the total number of tuples is too small. If you try to build bitmap index based on the ID, that's a bad idea. That means you have what? 100 entry, and all the entries has only one value set to 1. We don't use this one. We don't build the bitmap index based on, let's say, the primary key or the key that has high cardinality, because we are not going to get the benefit of this one. Clear what do you mean here? Bitmap index here, when you build this one, I need to find what the unique value that's associated with every single or the search key that I want to build the index based on. What the distinct value that's stored based on this data. As you mentioned, for the gender, we have a male or female. Here for the field F, maybe you have a 5, 7, and 8. So this means when you build an index here, I'm going to say for the value of 5, assume that we have 3 records, and 5, 7, 8. This is index. My index has 3 columns, or 3 entry. For each entry, I'm going to have the, let's say, since we have 3 records, 1, 2, 3, so I have a vector of 3 bits. 5, 1, 0, 0, 7 going to be 0, 1, 0, and 8 going to be 0, 0, 1. Something like this. Okay? Good. How can you use this one? Assume that we have this index example, that we have the jewelry data, and assume that the file that has 6 records. And I'm going to build the index based on A and B. I'm going to show, by the way, the jury, and this is going to be next slide. Anyway, so here, based on the A and B, I'm going to use A has only 1, 2, 3 values. That's nice. B has 3 values. That's great, because at least low cardinality based on the number of tuples. Okay, so I'm going to build the value here, one index here, based on A, 30, 40, 50, the unique value here. For each of them, we have a bit vector. And the bit vector contains the number of bits, depends on the number of records that we have. And only is going to be set to the one based if the value that in this record has value of A equal to the value that you use the search key here. So you have 1, 1, 0. What does that mean here? That means the value of 30 appears the first, the second, and the sixth record. And that's it. So we can build this one with the B2. You can say the value for the B here, it's going to be B, and it's going to be based on index here, and 1, 2, 3, 4, 5, 6, just to this will show you the idea how it looks like. We have foo, bar, and bars, and here you can set, for example, 1, 0, 0, 1, 0, 0, and etc. Okay? Of course, someone will say, we have too many zeros and 1. Yeah, we can combine them later. That's going to be great. But you're going to see here how it works. So that's what we did with the second one. Let's have our favorite example here. We have an age of salary in 1000, and I'm going to build my index, bitmap index, based on the age and the pages of the salary. In the age, you know that we have unique value 25, 50, 30, 45, and 50, and etc. And here we have 12 records, and you have to set the value. It depends. Only set the value corresponding to the record where the tuple has the search of the value of the, let's say the age is equal to 25. So the first, and I think 1, 2, 3, 4, 5, 6, 7, and etc. Okay? And for this record, the 7th one, the value here, yeah, it's nice. It's funny when you try to count, the record ID, and the record ID is already associated here, appears here. Anyway, for the 85 here, you see that's 85, only the 7th record that contains this value, and etc. So we build this one in the age, and they can build another index based on the, what's called, the salary. The interesting thing we're going to see here, how can you use this one in order to answer the query that we talked about this one before? So what if, I said, find the people who buy jewelry, such as the age, where the age equal 50 and the salary equal 100. How can you answer this query? When you say here, it looks like, remember we talked about the secondary index, we use a bucket. So instead in this case, when you have to consult the first secondary index, the secondary index is going to retrieve or return, let's say, the pointers to the tuple that satisfy the first predicate. Then after that, I'm going to consult, look up the secondary index in order to retrieve, let's say, the number, or let's say the set of tuples, or let's say the IDs or pointers to the tuple that satisfy the second predicate. Then I'm going to intersect them. Then I'm going to just retrieve the, let's say, the survival pointer to the record. The same thing that we're going to perform here. So here in this case, take a look, consult the bitmap index for the value of age equal 50. If you go back here, just the value of age equal 50. So we take this one into. Okay? Then the second one, they said what? They said the salary equal 100. Go to the salary and retrieve the search key equal 100. If you don't find the key, then you can say it's done. We don't have value here. We don't have, then you return blank, empty. Okay? Then you need what? You need to intersect them. So it looks like the set of pointers here, and the pointers on this record, intersect them, then it's going to be, when I say intersect, you have to perform what's it called, bitwise AND. So bit by bit. Okay? So 1 and 1 is going to be, 1. Okay? Perform this operation, give you this result. Now we need to retrieve what? The record number 4. The 4th record. Nothing else. You see that how simple using this bitmap index in order to simplify the process that we have. We're going to do this one the same. For the Oracle, that's what you're doing here. They build bitmap index, you can specify that. Postgres, they don't use this one. They don't allow you to build bitmap indexing. But they use the same technique. Most of the databases using this one in order to what? What's it called? The bitmap scan index. So in this case, when you try to retrieve the data here, I'm not going to build or retrieve the data direct. I'm going to build, looks like, a bitmap index based on this index that we have. Give me the list of, let's say, whatever set of pointers. Then I need to intersect them, and only I'm going to retrieve the survival pointer from the heap scan, or the heap file that store the data. We're going to talk about this one later with the query processing and optimization. Okay? What's the relation between the bitmap index and the multidimensional? index. Actually, can multi-dimensional nature of the bitmap index. That means it looks like the bitmap index can work as exact. You can, let's say, answer the multi-dimensional queries in a more efficient way. So the first one, partial match query. Remember that you give me either, you build my index based on two different dimensions, and they give you one of the dimensions. And then now, how can we answer this query? So find people for the jury who age equal 50. So the simple thing here, this is, I mean, the beauty using the index here, the bitmap index, just look up for the index till you will give you, I mean, retrieve the corresponding filter. Then now, in order to answer this query, you have to retrieve the record, the third, the fourth, the fifth, and the record number 11, which does satisfy the condition that we have. You see that just fetch this one and you retrieve the number of tuple corresponding tuples here associated with this vector. If I've said, for example, the range query, and gonna be give you like value, well, this is gonna be like a specific area, and ask you to retrieve all the objects within this range. In this case, I'm gonna give you, I mean, find all the people, for example, where the age is going to be between two values and the salary is between two values. So the first thing to do here, go to the first index or the age, retrieve all the tuple, the vectors, okay, or the entries that satisfy this condition. So the age greater than or equal 45 and age less than 55. That means you see age greater than or equal or less than or equal. So when I perform this operation, actually it's end, but when you try to perform this operation, you're going to be 45 and 50. So it looks like clearly that all these tuples here that must, I mean, either going to be satisfy 45 or the one that satisfies the condition age equals 50 is going to be part of the result. So in this case, I'm going to perform OR, bitwise OR. So this is, I mean, the result of the first part. For the second one, I'm not going to retrieve anything yet. I'm going to perform this one in the memory. Then I'm going to look up with the other table, which is going to be the salary here, and try to retrieve the corresponding tuple, or let's say vector entries that, or bits that corresponding to or satisfy this condition. Between 100 and 140, so retrieve all of them. So in order, the salary is going to be in this range, either it's going to be here or here or here or here. It's going to be part of the result. So it's going to be for or bitwise OR. This is the result, or let's say the surviving, you say tuples that satisfy record ID or tuple IDs that satisfy this condition. Still, I need to answer both of them. I need just to intersect the both tuples that we got, or the record ID or the pointer that I received from two different indexes. Okay, which in this case I'm going to perform the AND, and which in this case allow me just to retrieve a more efficient way. I can also what's called the range match query. So bitmap index works fine even for the second one. So the bitmap index fast for read-intensive workload, or mainly if you try to read the data, okay, mainly reading data, you're not going to die, you're not going to, perform insertion modification of the data, okay. And we said sometimes it's going to be often built on the fly during the query processing. We're going to cover this one starting today. We're going to take a look to the query processing. Then later, I'm going to show you that when you try to access the data, one way to access it, you're going to build, you try to use what's called the bitmap, okay, technique in order to access the data. You notice that we have too many zeros and too many ones. For example, we'll assume they have, you see, F1, F2. It looks like we have 100 records or 1,000 records, so maybe we're going to have too many zeros here, and maybe we have ones here. And especially here, if we have the number of, let's say, the domain size of the F is going to be too large, okay, compared to the number of records that we have, that means you rarely have ones here. And even if we didn't have ones, if you have too many zeros here, then it's going to be stored here in the index. And remember, you will build this index, somehow you're going to store this index on the disk. So it's going to reserve a place. So is there a way I can compress the data or make it shorter? Yes, we can perform this one. So we can compress the data. Okay, since the uncompressed index is going to be large, we're going to be reserved a lot of space. But we need to make sure that when you perform this compression technique, I'm not going to cover them with more details, just to give you a link. You can go over this one in your time in order to get more details about different compression technique. Okay? And you need to make sure that when whatever compressed data they're going to use, or compression technique, you're going to use to reduce the size of the data, make sure that you're still being able to perform AND and OR operation. It must be fast. don't come up with an algorithm that, okay, you reduce the size of the data, but the problem here, we try to perform AND and OR operation, going to cost you, you have to compress the data, you go with more computational, that's going to cause, that the overall performance is going to be degraded. We do have, as you know, two different types of the compression of the data. The first one, lossy and lossless. Lossy, that means you're going to compress the data, but we are going to lose information. Why do you do that? And some, you say, application or some data types is acceptable. You have to do this kind of compression. For example, if you have like an image or maybe you have a video, it's okay. You lose data that can be tolerated in this data or this application. But for the relational database or anything, if you have a database, if you lost one record or one value, that's going to be a problem. So we prefer to have what's called type of compression. You're going to do what? Lossless. You're not going to, lose any data while you compress and decompress the data. So the main goal, we can summarize, the database compression must be satisfied the following: must produce a fixed length value, small value, okay. Allow us to be efficient while accessing the tuples, okay, reduce the size. Allow the database management system sometimes to postpone the decompression of the data as long as possible during the query execution. Sometimes there's some compression technique allow me in order to do what? In order to perform operation even if the data is compressed. The third one must be lossless scheme. That means you don't delete or remove any piece of information. All the data, when you compress the data, if you uncompress, you're going to achieve the actual data. Okay, as I mentioned, depends on the application that we're going to perform here. Okay, so I'm not going to go over all that more details. If you have a time, I encourage you to take a look to the indexing technique in the main memory database system. We cover mainly here the database. We rely on the secondary storage medium in order to store the data. There is another database management system that mainly rely on the main memory in order to perform the operation. So if you have a time, it's not a few pages. If you can take or get at least give you an idea what different techniques indexing technique used in the main memory, that with the database management system, or that rely on the main memory. Okay, and those I think two papers can give you an idea about different compression techniques you can go over in your free time, and to give you an idea. That's all about the first part of today's lecture. So let me remind you what we did so far here. First, we have a data file. And we said, okay, this file or relation can be stored in the block or page in the disk, okay? Because we focus on the disk-oriented database management system. Then, in order to organize the way, in order to figure out how can we store the figure out, for example, the blocks or the page that belongs to this file, we add, let's say, special page. We call this one the page directory. Okay, then we looked at the way how can we organize the tuples inside the pages, the record itself here. We said here we have the page table, and each page is going to have the following format. It's going to have the header, then I have the array, slot of array. Then here we can store, the record from the end to the beginning, and the slots are going to be increased, or it's going to be from the beginning to the end. For every single page, we're going to have just to have a pointer to the beginning. For every single tuple stored in the page, we do have like a pointer to the beginning of this record within this page. In order to access any page or any tuple inside the data, we use the record or the page ID or the record ID, the tuple ID or the record ID, which simply can be page ID plus the slot within this page. That's what we did so far. Then after that, we look at the way that how can you fetch the block back and forth from the disk to the main memory. Because as you know, we cannot operate on any objects or to say any page on the block until the block of the page must be going to be in the main memory. Then we took a look to the way that how to use the buffer pool. Okay, and to show you a different technique. We have a page directory. This one is gonna like specific data structures that allow you to also know to figure out to find out whether the page exists in the main memory or not. If the page does not exist in the main memory, that means we have to fetch the page from the main disk to the main memory. Of course, we take a look to the different replacement policy, which allow us in order to, since we don't have enough space, or to say have a limited space in the buffer pool, maybe in the buffer pool if you have, for example, 3 frames or 5 frames, as it might be the case, all of the frames is going to be reserved, or to say be occupied by another page. So if you need another page to fetch from the disk to the main memory, you have to find or vect one of the existing pages in the buffer pool. That's what we cover in the replacement policy. And then after that, we build on the top here. How can we find or access the data more efficient way? In this case, what we're doing before any indexing technique, we're gonna do what? We're gonna go to the buffer. I need page 1, for example. You have to go to the buffer pool. In the buffer pool, you're gonna do what? To check the page directory, whether the page exists or not. If the page does not exist, of course, definitely we have the page, let's say, directory is gonna be stored here, okay? Directory page, it's gonna be stored here. This one is gonna tell me or how can we retrieve the page from the disk to the main memory, or at least all the address. Fetch the page and reserve a specific place into frame. Then after that, return, the pointer to the space, to the one that asked for it. The part of this one here, I might be required in order to perform like sequential scan, or maybe random X, in order to get the data that I'm looking for. So what I'm planning to do here, we're going to build the special data structure. So you are going to consult this special data structure in order to speed up the access of the data. So if you're looking for a specific page or a specific directory here, or to say so, or I'm looking for a specific tuple, maybe I'm going to consult this index, and the index is telling me that, for example, retrieve page 5, or retrieve page 16, or page 100, or whatever, or the tuple that you're looking for, you just to get access to the specific page. So this is a coding assignment 1, 2, 3, with the record, and coding assignment 4. Then after you're done from this part, there is no more coding assignment. Okay. Now what we're planning to do, since we'll try to give you an idea, how can we implement the database management system from scratch? Or in other words, implementing database management system is not easy work. So what I'm planning to do here. Then now, starting from today's lecture, I'm gonna see, for example, when you say select, start, for example, from let's say where, whatever you have a predicate, okay? How the database management system take the square statement, let's say SQL statement in general, so it's going to be anything, update, insert, or select. Then after that, how the database management system figure out a way how can be executed. So it looks like when you write any code and you're using any programming language, you're going to use a high-level language, right? Then after that, you're going to use a compiler or interpreter. It depends whatever programming language you're going to use. Then this one going to be translated into what? Into machine code. Then whatever the CPU is going to execute your command or your instruction, then give you the result. So now we're going to go in more detail. The same thing with the database management system. We start from the moment the user is going to type SQL statement until the database management system is going to produce or give us or generate the result that we're looking for, which is called the query processing and optimization.